Thank you very much. Thank you very much. So we are coming back to the sum session and starting from Krzysztof's presentation.
Okay, so hello again. Let me share the entire screen. Now you should see everything. So my topic and my presentation is about the reference implementation of generalized score distribution in Python. So let's begin with quick reminder, what is a generalized score distribution? So in a nutshell, it's a discrete distribution with support on integers, and its main feature is that it covers all possible variances. The distribution is parameterized by the expectation value, so have one parameter, it has nice interpretation, and the other one we can call shape parameter, is related to the variance, but for this kind of distributions, it's not simple, because the distribution depends, the possible range of variances depends on the expectation value. And the good thing is that the row is a linear function of variance, or variance is a linear function of row. So row 1 means that we have minimal possible variance. So like in this example, we have just ones, or something that is not concentrated on an atom, so like 2575. And the total opposite of this is row 0, which means the maximal variance. Like in this example, we have totally opposite observations, and the same case here with different means. Just to say what it is. Of course, we have many, in fact, infinitely many such distributions, and to be a GSD, or let's say DGSD, the one proposing the paper, we add an inductive bias that it is for subjective experiments. So the probability mass function represents something that we may expect to observe in the subjective test. And the RefGSD library provides two most important parts of this distribution. So this is a Python library. It's available as open source on GitHub. Here's the URL. One thing, the most important, is reference implementation of probability mass function for GSD in pure Python. And you may consider this as a source of truth if you want to implement GSD in the language of your choice. So this can be source of your unit tests, and this is focused on correctness. For efficiency, for numerics, we provide two most important functions, log, prop, and sample. They are implemented in JAX for efficiency. I will get back to this in a moment. And also we have some additional utilities, but they are not part of the library. This is a library, not a framework, nor an application, just a library. So it's a set of useful functions that allows you to build your own solution. And in particular, for a random variable that follows from generalized score distribution parameterized by psi and rho, we provide a probability mass function. So as I said, this is a pure Python, emphasized for correctness, well tested, and to that point that it has its own syntax to be as close as possible to the formulas in the paper. So this is correct always, but it's pure Python, so it's slow and it's not non-differentiable, and just for the reference. For more numerical parts, we have JAX, and I made lots of bugs, so you don't have to implementing this. And now you have log probabilities. So basically, you can efficiently compute log of probability in GSD, and this is again verified in unit test against this reference implementation. We provide sample efficient sampling mechanism, so bootstrap and then randomized algorithms can be easily applied here. For convenience, we have mean and variance functions, but they are quite simple. And we offer some of the fit methods. I will discuss this in the live code demo, because fitting this distribution can be sometimes tricky, especially if you want to use gradient-based estimator. And I will quickly show you the full documentation. You can go to this website. So there is a full documentation. Besides all the mentioned, we provide endpoint GSD experimental, which has some useful tools that are not just simple functions. So I said it's a library, not a framework solution, and I don't want it to be nor framework nor an application. Let's keep it simple, lightweight library. So we have this experimental where we have some more complicated functions, or something that maybe should be moved to another repository, or maybe it's not that polished, so maybe needs to be more tested, or documentation needs to be updated. So this is in the experimental, and parts from the experimental probably will gradually be moved to either different repositories or their own packages, or after improvement to the core GSD API. And now let's go to demo. So quickly, let's let me show you the repository. This is your starting point for GSD. You can go to documentation, and this is the main source of information. If you check the API, you can see we offer quite few functions for the things I discussed. So GSD prop is this reference implementation. Notice that I leverage Unicode support for variables to make even the argument names as in the formula. So it's easy, really easy to read this code. And now we have JAX functions with the full documentation. So this is API, and here you have 4 different examples. If you want to start from scratch, you just begin with this simple blank Colab demo. So just open this, and you have Colab environment with all the needed informations. As you can see, we can compute probabilities, use feed and moment estimator. One thing to remember, the package is named GSD, and you import this as GSD, but you installed ref.gsd, and this is because there is another library called GSD, and we were conflicting on PPI, so that's why we have to do this. Here we have a simple Bayesian estimation for the model, and because the model has two parameters, it can be estimated by simple numerical integration. So you can use this code to estimate uncertainty for the model. For different kinds of maximum likelihood estimators, we have this example where we leverage SciPy optimizers. So first we build a log likelihood or negative likelihood functions based on JAX functions, and here we leverage the JAX JIT for performance, for GPU, for speed, and we can use either bounded optimizers, or we can use TensorFlow probability optimizers to compile this. So everything is quite fast and reliable. One thing, for now we have only 5-point scale implemented in JAX. There is an ongoing issue on GitHub, so eventually this will be solved and the full GSD will be provided. So please stay tuned, give us a star so you will be notified once this is ready. And finally, the topic for today is here, and this is basic show how to use this package to do some experiments with to let's say analyze your experiments. I placed the content of the presentation here, so you have all the informations available here. And now we can quickly go to demo. For this, you can either go open it in Colab and run in Colab, but to be certain everything works, let me use my my own PC. So it will be probably faster. We don't have to wait for the runtime to initialize. And today I will show you how to apply the library to three parts, to three tasks. First, well, the obvious one, we can estimate GSD parameters, but they can be used for something more, and this more is we can compare to another experiments, like well-established HDTV experiments, or we can check the consistency of the experiment. And so let me quickly show all the steps. First, let's get the experiment data set. For this, I use Surel data that is publicly available. And I use experimental maximum likelihood estimator based on gradient. It's experimental because if you go into details in the paper, you will see that it is not smooth, and gradient based estimators are not really good in this case. But as you can see, it works, and we can forget this one. And notice I use here some useful utility functions like sufficient statistics and JAX with all the tools it offers is really useful and helpful for scientific computation. And now we have parameters of the model. Now let's compare this to TensorFlow probability versions. Very close match. So as you can see, a gradient-based model gives really good result. compared to Neldermet, which is derivative free, but also slower. And now, if you want to fit more parameters, you can use map function, give us the estimator. And the best thing from using JAX is that this is compiled, JIT compiled under the hood, so it's not Python. There is no GIL, no interpretation. This is just a raw power of CPU, GPU, TPU, whatever your accelerator you have, and JAX supports it. You can leverage it. So it's, you see, it's just 0.3 second to fit all the values. Let's now go to the comparing experiments. So for this, I have pre-computed parameters for HDTV data experiments, and now okay, this was another important. Here I will use another estimator. This is grid-based estimator. It's slightly lower in some cases, but this is the most reliable estimator. Basically, we have a grid of parameters, and this is 2D, so there is no curse of dimensionality. We can reliably use this estimator, and under the hood, it goes down to a simple dot product between vectors, so it is super fast and easy to parallel. So I will use this one in this demo. Okay, so I have all HDTV file parameters. Now let me use this new estimator to feed parameters for all the PVSs in this experiment that we are analyzing. For this, I use JAX VMAP with JAX JIT that produces very efficient estimator with batch semantics, and it's super fast. And now we can compare this experiment against to HDTV. So what we have here is well, basically it's scatter plot of psi and rho. Dots represent the experiment, and the ISO line are the joint distribution of parameter from HDTV. So basically, this shows you if your parameterization of the experiment is close to the HDTV or something else, or not. Basically, you expect your points to be around the mountains, and then rarely expect to see dot in the valleys of this plot. Okay, so, and notice that this is just artifact that we are moving above 1 and below 1. You can just cut this and get the proper. Unfortunately, Seaborn doesn't support this, but in R, this is done automatically. Okay, so the next part is consistency check, and this is done by a method of probability plot of G-test p-values. Details are proposed by Jacob Navarra, who is also I've seen among us here, and some of this code can be credited to his repository. So I use some of the implementation, in particular t-test, g-test, and the function for plotting. So let's see. There is a utility function ppplot data that gives us basically the p-value, and this is one of these razor sharp edges that is not well polished, well documented, but it's ready to be used, and I expect it to be maturing over the incoming weeks. So now let's run this experiment. It's quite fast because now I have 99 bootstrap samples. For real experiments, you can check the paper, but the values like 4.9 are recommended. And now we can plot this empirical CDF of the p-values compared to the uniform CDF, and in general, for consistent test, they must be under this margin here. So we see this test is correct, this experiment, and now I have an experiment which is not. It's slightly larger experiment, so let's get the data set. Again, let's repeat this bootstrap. It's slightly larger, so we may wait a few more seconds, but not that much. Okay, and we got the plot above the line, and this is what Lucian suggested. This is from different labs, different scores, very non well behaved tests. I was taught so. So this was what we expected to see.
Well, the test well behaves is just from well, it's more complicated, and it's also in virtual reality, so we kind of accept that that the scores won't be so regular like in a traditional experiment.
Okay, thanks for clarification. And that's it for the live code. And again, this is available here in VQEG, so you can basically substitute this cell, load your own data set here, and just press run all, and all the analysis should be carried out, and you should get the results. If something doesn't work, so let us know. Feel the issue on the GitHub. If you want to add something, feel free to add pull request. Hopefully, the documentation is well written and can be useful for this. I said that this is just a library. There is one simple exception. If you call it in this way as a module with a command line option, this gives you the estimates for the moment from the moment-based estimator. So we have two parameters. You can compute variance and the mean, and from this we get the two parameters. But in general, we do recommend maximum likelihood. Especially the grid search one is really correct. We will be working on improving maximum likelihood by gradient method, and also you can expect some additions here in regard of Bayesian estimation. Let me check if there is something here. Okay, do you have any questions?
So it's a time for questions. Okay, I don't see any questions. I think that as a tool for fast ppplot analysis, before we were not able to do it so quickly. This is nice because it's a really simple way to show that your experiment is kind of in line with a typical subjective experiment, or maybe it's not, but there is a chance that there is a good reason for that. For example, the experiment is more complicated. And also this comparison with HDTV, I like it because it gives you one plot that really shows how much different you are from, again, very typical experiment in the behavior of the subject. So I recommend to use those two in some publications showing some data sets.
In the future, we may extend this to add some command line utility that, given the data set, will produce you both the comparison to HDTV, ppplot, and maybe some summary statistics in one PDF file.
Yeah, there is a chance for that. Okay, thank you very much, and we can move forward to the next presentation, which is again a tool presented by Lucas from Netflix. This is a tool to produce the data that you can then use and analyze with GST. So please go ahead. Thank you.
Now I should be unmuted. I hope everybody can see my screen. Thank you so much. So this is a presentation of a platform called E2Nest that was developed mostly by Z, and I contributed just a little bit to the development. So he was supposed to present this, but unfortunately he cannot make it. But his presentation is still available. It's really nice, crisp, technical presentation that you should have been given today. But unfortunately, since I am the one presenting it, the presentation actually looks more like this. Excuse me. Yeah. So it's going to be full of poor attempts for jokes, some memes, and I actually tried to use as many references to my favorite shows as possible. So bear with me. And the good news is that if you are more interested in the pure data, you can still check out the original presentation. Because this is going to be mostly just an introduction, and I would like to get you excited and show some of the use cases and especially explain the most fundamental concepts. But everything is very much detailed in the original presentation that also is GIF-less for those of you who hate those. And there's also an instruction memo with examples that is very, very useful if you really want to run an experiment, so that you can check as well. And obviously there's a GitHub project that has a README and a good documentation. The link to it is added as well. And if none of that helps, feel free to ever contact me or Z by email or by any means. So yeah, check out these resources because this is not going to be a complete. So this is just a disclaimer. Now, first of all, what is E2Nest? So it is a web-based platform for media-centric subjective testing. Originally, we developed it internally, but now we decided to open source it under a BSD 3-clause license. So the code is fully available. The name is derived from Earnest Netflix Subjective Testing, because why not? The question, why do we open source it, is, first of all, we believe that subjective testing is really important to many communities. And open sourcing can help, let's say, reduce some overhead for researchers that are not specializing into development of subjective tests. We're also heavily invested in AOM Media, the Alliance for Open Media, that has a need for more continuous subjective testing, and it's important for it to be easy and so it can be repeated frequently. So we hope that that's going to be of benefit as well. And overall, it's to have a paved path for subjective tests, mostly to reduce this overhead and learning curve when you want to set up an experiment. Also, one good thing about this is that we have a playlist logic that automatically assigns the stimuli to the session for the subjects, so you don't have to do it manually or have some ad hoc scripts. There is some logic I'm going to be talking about, which we believe could be useful for a lot of people, and again, make everything simpler. And also, this is a platform that could be like a backend, and then you can bring your own UI or whatever look your experiment should have, or whatever methodology there could be. But you can still use this as basically a powerful tool to save the results and then export them in formats that are basically compatible with workflows that we have, like Surreal, etc. I'm going to get back to it as well. Now, what is it capable of? I wouldn't be as cocky as General Kerrigan over here. We cannot do anything, but it definitely is flexible. So it covers audio, video, and images, and it's built upon modern browsers. So it rides on the top of their codec supports. So we can support AV1, HEVC for Chrome and Safari, for example. You can also support Dolby Vision and HDR10 on an HDR enabled devices such as MacBook Pro. It does support major subjective methodologies. So currently we have ACR, DCR, two alternative force choice, Sandvik, and a bunch of others. Also in a standard compliant mode. So you have like one more interactive mode, and then a mode that is really having this grayscale or gray screen, then the stimulus, etc., etc. So this is all implemented out of the box, but also we can customize it because it's basically HTML based. So we can change the way that the text looks like, anything. And yeah, you can bring your own UI and just wire it together with the backend. It is useful for, well, we are envisioning expert viewing, in-lab control tests, as well as crowdsourcing, depending on how much limited you could be by the fact that it is browser-based. And it's definitely useful as a testbed for more advanced subjective quality research. So we have heard a lot of talks about statistical data post-processing from Loic yesterday and today at SAM as well. And there is also ongoing research in active sampling, so how to maximize the information value of each observation. I believe this is a useful tool for all of these research directions. Now, what it allows is also two modes. First is the standard configuration mode, where everything is hosted at the server. So for example, in an instance, and that's including the media files and the database, the backend database. And then on a client side, the only thing that is used is basically the browser. This is, as I said, a standard configuration that works fine for most use cases, but you can imagine that if you have large files or your connection is not expected to be stable, you need to have some insurance that the videos will be there on time to play when they need to be played. So there's also a special configuration that allows pre-downloaded videos hosted on a local test subject's computer. So both of these regimes are allowed and work fine and are tested. So depending on the application, you may choose one or the other. Now, I'm going to talk about some key concepts that will be necessary then when we are talking about how to actually set up an experiment using E2Nest. There's one Easter egg over here. So first of all, we define an experiment, which is basically a subjective test that has its own unique identifier. Let's call it, for example, eTunes demo. Then we have a session, which is basically each experiment consists of many sessions, and each session corresponds to a single subject. So subjects can come for multiple sessions, but each session is mapped to one subject. And in each session, there are multiple rounds, and rounds is basically, let's say, the act of voting during the round. So you show the stimuli, and then you ask for votes, and that's called a round. And then we have a concept of a vote, which in each round, you vote one or more votes. Here is the example of what it looks like in terms of one-to-many mappings. And as an example, we can see what it looks like for different methodologies. So in ACR, you have one vote per round, DCR the same. MLDS methodology, for those of you who are not familiar with it, it's the one where we show you 4 different stimuli at the same time and ask you if the top or the bottom ones are closer together. So it's basically like a forced choice, but based on the 4 stimuli, but you still have 1 vote per round. So you show 4 stimuli, but you get 1 vote. And in SAMVIC, it's actually multiple votes per round, because you have a reference video and then you have access to multiple distorted videos at the same time. And then the round is considered to be finished once you evaluate all of these videos that are available for that particular reference. Now, when it comes to general test procedure, what happens is that the subject signs into the system using the credentials that the administrator created for them. I'm going to come back to this later. And they start the session. We call it the session Y here, for example. And then this subject is shown instructions. They are shown training, if there is any. And then there's actual test that is consisting of multiple rounds. And at the end, we also allow to show a survey if, for example, we want to have some demographics information, etc. And then there's an end of the session, and we do it over and over and over again until we reach the number of sessions we are happy with. In order to understand how the config file for each experiment is created, or sorry, how we put the content in the experiment, we need to define these concepts as well. So first of all, we have a content, which is a source or a SRC. It's a source signal. So where does the videos that are in the test come from? And then we have a stimulus, which is a PVS. So each stimulus is a processed version of a source signal. Actually, even the reference is still considered a stimulus because it is shown. So whatever is shown to an observer is called a stimulus. And then we have these 2 concepts that seem complicated at first, but bear with me and hopefully they will become clear. So first of all is stimulus vote group, where 1 or more stimuli belong to the vote group. And then when the vote is casted, it is relevant to this group of stimuli. And then we have a stimulus group, which corresponds to 1 or more stimulus vote groups and 1 or more rounds. Now, as I said, this looks complicated, but it's going to be quite, let's say, transparent when we do the examples. So in ACR, we see 1 video, we vote on it. It's 1 video per stimulus vote group, and in 1 video or 1 stimulus vote group in stimulus group. In DCR, we have 2 stimuli in stimulus vote group because we have to show a reference and a distorted video. So we have to show 2 stimuli, but they have only 1 vote corresponding to them. So SVG equals 2, and the stimulus group there's just 1 stimulus group. In MLDS, when we have the 4 stimuli, we show 4 stimuli, but we have 1 group per the group of stimuli. So 4 stimuli in SVG and 1 SVG in SG. Oh, this is going to become really, really frustrating, I guess, if I use these acronyms. But mostly, and this is the reason why this is sort of complicated design, is for SAMVIC, where we have a stimulus per stimulus vote group is always, there are 2 stimuli. There's a reference and the distorted video that we are trying to evaluate. So they need to be collected together in a stimulus vote group. So the votes are always relevant to the pair of the reference and one of the videos that was selected from the list that are available. But in each round, we do have n stimulus voting groups per that group. So the group is created actually from all the stimuli that will be showed in that one round. So as I said, this is why the design had to be a little bit more complicated, but it gives us a lot of flexibility when it comes to different methodologies and different relevance of votes to a particular group of stimuli. So it allows us to make this perfect mapping from whatever vote actually goes to and when it is shown. The reason why I am spending this time to explain this is that when we are configuring the experiment, we will be defining these stimulus voting groups, but most of the time it's very uncomplicated because it's just ACR or DCR. Now, how do we set up that experiment? And I totally understand that this GIF is very much unrelated, but this was the only thing that I could get to set up. So sorry about that. If you don't find it funny, I do. Now, each experiment is defined by a config file, what I mentioned. And in this config file, we have two big parts. One is the stimulus config. So how do we configure the stimuli? And there we define the paths to the contents and the stimuli themselves, so where to actually look for them in the server. And then these stimulus vote groups and stimulus groups. So basically, what are we going to be showing together and what is relevant to each vote. But the good thing is that you don't need to do this manually. This is quite automated, but it's still important to understand these concepts from the design perspective. And then we have a configuration of the experiment, which is basically just defined by a title, which is a unique identifier. Then you define a vote scale. Currently, we have something like continuous 5-degree scale. We have discrete 5-degree scale. We have continuous from 0 to 100. We have forced choice and a bunch of others. There's a list in the GitHub project. You define a methodology for this, which also we have a bunch of, and it could be extended for whatever methodology anybody can use. And then we define how many rounds are there in a session for each observer. So for example, if you want the person to see 30 rounds, 30 stimuli, we define it as in here. Then it also allows us to put some additional pages such as instructions and instructions for training or the survey at the end. And then there's a couple of more playlist related entries that I'm going to be talking about in a second. So the playlist itself is mostly the most painful part, I would say, when creating the experiments. And that's why we are trying to make this automated, but in order to make it sort of optimal and also flexible, we need to configure a few things. First of all, it's a random seed. So how much do we want to randomize? And most of the time, I think most people will be using fully random playlist. So fully randomize the appearance of the stimuli. Then we also have a prioritized list, which is basically something that is exempt from the randomization. A typical example is training or reliability checks, where we do want to put them in a certain spot. So for example, for training at the beginning. So we don't want a randomization to touch these stimuli groups. Then we also have the groups that are used for these particular cases, such as training or reliability checks. So we exempt them from the randomization, so they are not put into other places. And we also have an identification for the training rounds, which because they are sort of special there. In an example, we will want to have training always at the beginning. So we say that rounds 0 and 1, there will be 2 rounds of training, and we're going to be using the stimulus group 3 and 4. So the pair of reference and distorted 3 and 4. And then we want to randomly pick around somewhere in the session that we will put a stimulus group 5, which is used for reliability check. And in order to achieve this, we would specify something like this. So we want a random seed, which is saying everything else is random, but we have a prioritized round 0 and 1. There we'll be using stimulus group 3 and 4. And then we have a round ID null, which says anywhere in the session, just also put stimulus ID group 5 that is going to be used for something else. And then we blocklist these stimulus groups ID, so these stimuli will not appear anywhere else. And then we define that the training rounds are the 0 and 1. So this is sort of, let's say, an example of how we would normally put some of these information in a playlist whilst it remains completely random. Now, after we create this config file, there is a command line tool that allows us to set up the experiment and interact with it perfectly. So first of all, we can even check if the config file is valid for example, methodology with that particular scale, etc., etc. There is a check for that. We can then create a new experiment, and once we do that, we assign it to an administrator. And if we do not have the administrator in the system, it automatically creates credentials for administrator that then can go into the system and interact with the backend, check out the database, and also do all these other actions such as creating new sessions, etc. Now we can add a new session for a subject that is going to be automatically created, or we can create a profile for the subject, like the credentials, and then we add new sessions to their profile. So there's a command line tool for that. We can delete sessions by sessions IDs seamlessly, which will automatically be addressed in the database, etc. If somebody, for example, cancels. We can delete an experiment by a title if we want to. And also, yeah, if we want to create a bunch of different, let's say, usernames. So we want to, I don't know, have a crowdsourcing, and we know that we need different addresses, that we can do it in a bulk at once, and we can set their passwords to something random, and then ask them to do it themselves, to change the password for the future users, etc. So this is all possible. It's not necessary, because also this command line tool is convenient, but you can do all these also from the system. So when, as an administrator, if you set up the experiment, then you can go into the system and you can manually add new sessions, add users, etc., etc. Now, what I find really cool is the playlist logic, because as I mentioned earlier, I do believe it's pretty painful to do it manually. So I find it really a good piece in here. And the good thing is that we assign it optimally to each round automatically. So what I mean by that, we reduce this planning overhead of thinking, oh, what should be watched when, by having some sort of rules that optimally put what stimulus group should be up next in the next round. So when we are creating a session for an observer, it looks at what has been done in the past, what stimuli have been viewed by the subject and by other subjects, and automatically creates a list of the rounds that are going to be providing us the best coverage of the stimuli space. Now, there was a number of careful design considerations taken into account when devising this methodology, and I'm not going to be covering them all, but Z has them in the original GIFless presentation, so feel free to check it out after. Now, for a non-active sampling case, we have this sort of procedure, and let's say this is going to be very loosely speaking. You can check out the code if you want to know how exactly it works. But basically, at the beginning, we want to know what is the random seed, what is the prioritized list, so we can exempt it from randomization. What's the subject? and like who is the subject who's going to be evaluating, and who's the session created for, and what's the playlist determined until that point in the experiment. So how many stimuli group have been evaluated, and which one of them. And as an output, we're going to get a list of rounds that the subject is going to be evaluating next. And the procedure is pretty simple. Basically, if there is a prioritized list, if there are any stimulus groups specified in there, we add them to the session straight away because those are exempt from any other logic. And then we check if the subject already voted previously on certain stimuli. And if they did, we deprioritize these and we add rather something that the subject hasn't seen before. And secondly, for the remaining slots, we added from the list of stimuli that were randomly picked from the remaining stimuli groups, but we're prioritizing those that have overall lowest count, so who most people haven't seen yet. So this is sort of a very loosely speaking, the procedure of how we automatically add these rounds to the playlist. And at the end, we save this relationship of round and stimuli group to the database. Now we also have a potential for active sampling case, even that is not have been implemented yet, and there are multiple ways of doing this. But the idea is going to be the same. The input is basically we need to know exactly the same thing, but also we need to know what is the test outcome until that point. So we need to process all the results and input it to this logic. And then as an output, we're going to get the same thing. We're going to get the list of rounds that are the most, and they are going to be providing the most information. So currently this is not implemented, but all the wiring is done. It's mostly just to have the backend logic there based on the active sampling strategy that we want to use. Now, when it comes to the results of the test, the administrator has a very convenient way of getting those even throughout the process. So it doesn't have to be at the end. When the admin signs in to the system, they see something like this. So they've got a list of all the things that have been defined. So experimenters, subjects, their votes, everything is in a separate list. But if they click on experiments, they will get a list of what experiments are there created for them. There's and then for these tests, you can always download the data from the database. And there are a couple of options, or 4 options actually. One of them is serial compatible paired comparison format. Second is serial compatible DMOS format. And then there's this thing called nest format, which is basically E2Nest's own JSON format that is more relevant to the concepts that I defined, like the stimulus voting groups and stimulus groups. And it's pretty easy to read that, for humans, I would say. And then there's also a CSV plain format. So all of these are exported and are already in a way that is compatible with, for example, Serial, that then just allow to simply run the processing scripts on them. So coming back to the main takeaways, and that's something I would like you to take from this presentation today, except for that GIFs are either cool or not, depending on a personal preference. I would like you to remember that ETNest is cool, and it supports a bunch of use cases and allows for a lot of extensions. It's simple to run an experiment with it just by creating or modifying an existing configuration file with all the concepts that I have tried to explain today. And if I did a poor job, again, check out the other materials. Those explain them hopefully in an even more concise manner. We just add subjects and sessions via a command line tool or in the browser to this. And then subjects just automatically see their sessions if they sign in with the credentials that are created automatically. And the result can be retrieved in a number of formats that are also compatible with, for example, Surreal for convenient further processing. One last thing that I would like you to take away from this is whenever you forget anything about what I just said, there's a lot of material, especially the detailed presentation and instruction memo that are linked here. Now, what did we not cover today is how we can add a different subjective methodology. How can I change the look of my test, or how do I set up a hosting server, or how does the Django web framework actually work? What are the modules in the E2NS? These are all for like material for their own presentations, and they are covered in the material that I linked. So feel free to check them out, and or feel free to ask me about any of these later. Thank you so much.
Thank you very much for so many information and gifts and all this. Any questions? Please, Ludo.
Thank you very much, Lucas, for the presentation. I was wondering how much effort you put into the actual presentation of the video on the display. Things like how do you check if there's been rescaling on in the web browsers, how to enforce the full screen mode, and so on.
Yeah, this is a very good question. And so normally we do have a full screen mode, and also you have this, you can do it in the design of your own experiment. So because you do decide how this is going to be done. You do create the whole HTML. When you have the methodology, you do create the HTML page that then decides if it's going to be full screen, if it's going to be, changing the aspect ratio, if it's going to be just in the middle, and so on. So this could be the design. So by default, I think we do full screen, but it is modifiable.
Okay, thank you.
Okay, thank you. Andreas?
Yeah, thanks for the presentation. I think it's really formalized really well. GIF are perfect as well, really illustrative. But I think, like from what Ludovic Malfay said before, I think, or also because from last time when Z presented that I understood it was more like for in-lab or inside Netflix or inside any company, like control environment. But when you go for crowdsourcing, do you think it's possible to add some module that will track behavior of people, like how long they stay to read the instruction, or if the video playback is smooth, or anything like attention, if they are changing browser tab, or like pausing the test in a way or doing something else, or how much we can integrate that and how much we can retrieve the data in JSON or whatever format that could give us some intuition on that. Yeah, thanks.
Yeah, this is a really good suggestion and something that has been brought up in the past. I think there's definitely a way to do that. It's not that it will be more difficult, and the JSON format should allow for it as well. So we have considered that. It has not been added yet, as far as I can tell. So all we added right now is the support for the honeypots, or the reliability checks, whatever we want to call them, that we have. The timing, I think that's something that is on the top of the list right now, but I don't think it's in the code yet. But it should be easy to done, and it should be possible to save it in a JSON in a database, just adding an entry. But yeah, it's a good point, and yeah, also it's an open source project now. So if somebody would find this interesting and could contribute to this, we would be more than happy to collaborate on that.
Thank you. And Dietmar, please.
Yes, yeah, thank you very much for this wonderful presentation and the offer to make this available to the public. We have done lots of crowdsourcing tests, experiments, and it's always the same thing that it takes so much longer to set up the user interface and to get this running and debugged. And so a system that takes away all this burden would be really, really helpful. Now, it seems to be very complex, offering many features, and my question therefore would be, what if I now propose this to a student, say, let's say a master's student in computer science, to show them, okay, here's the link for all the documentation, and here's the idea for an experiment, and here's $200 that you can spend on AMT or some other platform. Go ahead and in 2 months implement this test and then show me the results. Would this work, or have you done such tests maybe yourself, giving it out to people that are not engineers in your own group?
So I did not try with Mechanical Turk, but what we have tried is to basically do it with some employees. So we did a large test that we basically created credentials for people with their email address and the passcode they could go to do it. When it comes to designing the experiment, it's super simple. It did maybe I was looking at the presentation yesterday. I was thinking, oh, it may give away a wrong message that is too complicated because all the design choices. But basically, if you look at a config file, it's very simple to understand once you grab these concepts, how to set up another experiment. So with the master student, what they would do is they would look at the demo that I linked there. Basically, it's called the instruction demo or memo, instruction memo with demos, sorry. And that one has a step-by-step guide on what to look for, what does the screen look like that you click on, and what you will see, and then how you set up the experiment itself. So I would be confident that they would be able to do that. The connection to the Mechanical Turk might be something that we haven't explored properly. So I don't really know what are the limitations there. But as long as the users have, ability to subscribe or sign into the system, it shouldn't be an issue.
All right, yeah, thank you very much. Maybe I'll try it if I find a student.
Judah, you have another question, I guess. Or you've forgotten to?
I might have forgotten, sorry. But I can still have a comment. I mean, I hear that a lot of people seems to use the MTurk for testing video, for testing, for conducting video tests, sorry. And I didn't have time to create a slide deck for this meeting, but we've discovered very recently that many users are actually are using MTurk from India, right? That's not very surprising, and a lot of people are using VPN to hide their IP addresses and pretend that they're in the US, for example. But one of the big issues, and I think it has not been covered anywhere, and you've got to be careful, is that a lot of people are using remote desktop. So a server based in the US, and they're basically taking the test from India. And this creates transcoding, for example, and this is a big issue to me if you're running video tests. So I think it's a generalized problem on crowdsourcing platform. It's not just MTurk. I've been writing a paper on this, and I think hopefully it's going to be published at some point, but you've got to be very careful. Thank you.
Yeah, I think this is a very, very good point, and something that overall we need to be more careful in the industry on how we are testing for these things and how literally we take the data that we get from these tests But I think that a lot of people, at least in this room, do understand the limitations of crowdsourcing in general. And there are, in my opinion, there are also applications where crowdsourcing is just simply not applicable because of all the unreliabilities that come with it. But yeah, this is a platform that potentially can be used for that as well. But our main use cases were mostly the ones where you want to run quickly a test with students, with employees, with someone, and now you or with experts, and you want to quickly distribute it without all the overhead of creating the playlist and creating a UI for it or having a VLC playlist. It's just something that once people get a gist of it, will be speeding up these things massively. And there's a potential to integrate it with Mechanical Turk, but right now there is not maybe even enough protection, I would say, from like understanding what's going on in the crowdsourcing yet. But definitely this is flexible enough to be extended to that direction.
Okay, thank you very much. I guess there's no more questions. Although you just forgotten to turn off your camera and okay. So we have next presentation. Thank you very much for this one. And the next is from Dietmar and Simon. And this is national difference in image quality assessment. So this time we'll hear about the differences with using scales.
Yes, yeah, thank you very much. I hope you can see the slides. And yeah, so this is about national differences in image quality assessment, and we're talking about crowdsourcing data. And this is joint work with Simon Delpil from NTNU in Gjøvik in Norway. So here's the overview and the motivation for this. So people rate image quality differently, as we all know, and this is also the reason why in P913 and BT500 these subject-specific features like bias and inconsistency were introduced. And but this is not only the case for image quality, but in culture in general. So cultural psychology found significant national differences in many various areas. And our hypothesis is that, okay, these similar differences exist also in the perception of image quality. So not only subjects perceive it differently, but we can group the subjects into nations or cultural contexts, and then try to see if there is a certain bias or certain features that we can extract significantly and which differ then from country to country. And so we're investigating statistical models with these country-specific components for 3 large-scale data sets. This is a Conic 10K, 10,000 images, 1 million rating, Cardiff 10K, and NIVD, the Netflix International Video Data Set that was introduced just this year earlier than at QMEX in Ghent. And if there are such national differences, then they could be relevant for the design and analysis of future crowdsourcing studies for image quality assessment, of course, and also useful for services to adaptively stream content worldwide where they stream to different countries. Now, there are some previous work on this. First of all, I should mention this paper that introduced at QMEX 23 the Netflix data set measuring and predicting perception of video quality across screen sizes with their crowdsourcing. And in this work, they had a very large data set, 14,000 subjects, well balanced over 4 countries, and they noticed that there are biases across nations, but they didn't analyze this in further detail. And so Xi actually suggested to me, oh, why don't you look at this? And I told him, yeah, we need the data set, and then he made it available. So we're very grateful for that. Then there's this much earlier paper by Margaret and Lucian and others in this journal, where they also had a very outlined or strict protocol for experiments, collecting 10 data sets from 4 countries, and but there were many contexts that differed in these data sets, and the country was just one of them. And so their finding was only preliminary, that data sets appeared not to be influenced by language or culture. So that's there, different from the previous paper. And then also there's this paper also at QMX 2015, I think, where they detected significant differences in perceived video quality between subjects from 4 nations. But this was only a detection and not a further analysis. And so we try to present here now analysis, a model for such differences. Okay. Yeah, so in a visual quality assessment, there's a dominance, of course, for ACR and also for visual analog scales. We all know the ACR scale, and the visual analog scale is a quasi-continuous scale from 0 to 100, let's say. And users select a slider position, and then the position on the interval will be read off as a rating. And from this, mean opinion scores will be calculated either directly, playing scores, or with a subject model according to P913. Then it's a more reliable estimate. And so all the examples of the 3 data sets are of this sort. Conic 10K is an ACR data set of blind image quality assessment. CADIT 10K is a DCR data set, and NIVD is a video data set using the visual analog scale, or this is a SAMVIC procedure, actually. Now, previously, in the 80s of the last century, there was already quite some interest in finding out about these categories in ACR. CCIR proposed them, and from bad to excellent, and then it was conjectured that, okay, we should look at how these are perceived in the population. And there was one experiment in 86, which is presented here on this slide, where the experimenters put just a ruler on a paper and gave it to subjects, and they were asked to mark on this interval from 0 to 100 where they would place the bad, poor, fair, good, and excellent. And they did this in several nations, in several countries. And so here's just the result of Italy versus US. So on the left side of this interval, you see the 5 ACR categories as they were seen in Italy, and on the right you see them as they were seen in the United States. And so, so the result is quite clear. Obviously, these levels are not equidistant. They're not 1, 2, 3, 4, 5. They are fair and poor are much closer together than the others. And then also this other conclusion is that they differ from one country to another. The language differs, and then the perception of these words, where they are on the latent quality scale, would also differ. And so this suggests that there should be a country-specific model that takes this into account. And for this, we designed parameters that are these thresholds between these categories. And so these thresholds are what we call tau 1 to tau 4. They are on an interval, and they differentiate between the categories of the ACR classes. Now we have 2 types of models that we were using for our analysis. The first one is a Thurstonian model, where the quality of an image is regarded as a Gaussian. This is the same as in P913. So for the Gaussian, we have a mean and a variance, and that's then a random variable Q, which gives us the random effect of this particular image. Let's say the following here. So there's a global unique perceived image quality Q, which would be then the mu J for the jth image, and then sigma would be the variance around it, giving us the random effect. And then there are these country-specific ACR thresholds, which we propose here. They depend on the country K, and there's 4 of them. And then we also introduced one more thing that, well, we did this at the end when we found out that there are some problems with the data analysis if we don't include something like a global lapse rate. Now, lapse rates were not used so far in Estonian models, however, they have been used when assessing psychometric functions like in Quest Plus or Quest. There was a lapse rate in there. A lapse rate means that, okay, if the lapse rate is 0.1, then there's a 10% probability that the subject has a lapse or a finger error and just presses any one of the 5 buttons or chooses any of the 5 ACR categories with equal chance. And in the other case, with 90% probability, the rating will be according to the model with the Gaussian probability distribution. So here's a formula for this, and F then would be the cumulative density function of this Gaussian. So you just look at this graph here. This is the black curve is the perceived image quality on the latent quality scale of the participants. And we have these thresholds tau 1 through tau 4. And so the probability for choosing fair, for example, would be the area under the curve between the two thresholds tau 2 and tau 3. This is not accounting for the lapse rate that comes on top of it. Now, when you do the reconstruction for this, it's well known that the result will be invariant with respect to translation and scaling. So there are 2 degrees of freedom that have to be fixed or anchored. And so it's a good suggestion to just fix this by choosing tau 1 to be equal to 1.5 and tau 4 to be equal to 4.5. And that aligns the scales that we reconstruct to the common ACR scale, which goes from 1 to 5. We could have chosen -2 to +2 or anything else. And I will get back to these points at the end. The other model that we do is a binomial model, which tries to address a different research question. Namely, there are extreme response styles. Some people prefer choosing the most extreme options on the rating scale, 0 or 1 on an interval, or 1 and 5 in the ACR or DCR scales. So we devise a binary variable called extreme. It's a 0 if the rating, the ACR rating is 2, 3, or 4, or it is 1 when the rating is 1 or 5. And then we are asking the question, is there a significant difference between the nationalities of the raters in the IQI quality ratings with respect to this extreme performance or these extreme ratings? And for this, we use generalized linear mixed effect models. It's from the binomial with a logit link function, and that would be here the formula here. So essentially, we have a factor, a coefficient alpha k that says, well, in this country, the ratings of an image would be governed by this, and then there's a random effect which is then due to the image. So this accounts for all, for the uncertainty that comes with the image. And so there's a fixed effect for the country and a random effect per image. This is a little bit simpler than the other model, the Estonian, that has many more degrees of many more variables. So for the computational methods here, for the Estonian, we use maximum likelihood estimation. These are all the parameters. So we have for each country K, those thresholds tau m, m equals 1 and m equals 4 were already fixed, but the other 2s are here, tau 2 and tau 3. Then mu j are all the image qualities. So we have 10,000 of those for conic and cadid. Sigma is a global uncertainty, and a lambda would be the lapse rate. To optimize the function that we need to optimize, to minimize the negative log likelihood, we use an interior point method, which was implemented in MATLAB in the function fmincon. And for confidence intervals, we use the asymptotic Kramer-Rao bound. For the binomial model, we can use the Bayesian off-frequentist analysis, and the results reported here are done in R using the LME4 package or the library. In MATLAB, one could use FitGLME. And the parameters are then these country-specific components or factors alpha k and sigma. Confidence intervals could be or were computed with the Wald method and also a bootstrapping, which gave the exact same result, almost the exact same result. Okay, so now come to the data sets. So this is a slide, an overview. The table here says, okay, how many images or videos are in the data sets, how many ratings were collected in the crowd, how many subjects participated, and how many countries were participating in this. So in Conic and in CADIT, we didn't have any restrictions, and so we allowed everybody in, and there were like 70 countries, but many of them contributed only very few ratings. And so we restricted this to the 4 most prominent countries, which were India, Venezuela, Russia, and Serbia for Conic, and for CADIT it was Venezuela, Egypt, India, and Russia. It was mentioned before by someone that Indians, may dominate the crowdsourcing platforms, and this was the case here. And Venezuelans were dominating the second one. Okay, and then there's a 5th column collecting all the others. We lumped them all together in 1/5 country and calculated the parameters for these there. And here's the number of subjects. And I don't have the number of subjects for CADIT. I didn't have the time to do that. And down here is the Netflix study, which is much better designed in terms of a uniform distribution of ratings and the participants from countries. So it's almost uniform. Okay, here now the results. So for Conic 10K, first for the thresholds, these taus. You can see this in this table, but maybe it's better just to look at this graph down here. So horizontally, we see this interval from 0 to 5 or so. And these categories on these intervals of poor, fair, and good are listed here. And we do see that the interval lengths are different between the different countries. So the finding is that the ACR interval for fair is widest for India and smallest for Russia. And the variance, that's not shown in the graph, but you can see it here in the last row of the table, is largest for Venezuela and smallest for Russia. And note that the confidence intervals that we have here are very, very small. So this seems to be quite a good model and a significant finding. And for CADIT 10K, it is similar. Oh, I forgot to mention the lapse rate. So the lapse rate was only 0.5% here. That would help to stabilize the numerical procedures. And it's also a reasonable number. It seems to be okay. And here for CADIT, the lapse rate is 0.008, also very, very small. And also here we have different lengths of these ACR category or DCR, in this case, DCR category intervals. And so the interval for slightly annoying is smallest here for Egypt, for example. And the variance is largest for Venezuela, just as for the Conic 10K situation. Okay, so that's those 2 large data sets. And then here for CADIT 10K for the extreme ratings, the other way of analysis gave the following results. First, we selected countries and images to go into this analysis. So we selected countries that have at least 1,000 ratings for the images considered, and each image would have at least 500 ratings, and to ensure a large population there. And then we have 7 countries left over with 67 images in this part for the analysis. And now these are then the probabilities of an extreme rating in the different in the data sets from the different countries. And we can see that there are significant differences. So in Russia, the probability of the data set was the largest, and the smallest was here in Egypt. So this confirms the finding of other psychological studies that have found extreme ratings to be relevant between countries. Now the last data set is the NIVD data set, the Netflix international video data set is the following. So we took the data from the VAS scale and first looked at just the MOS and the scatter plots, country versus country. So a very simple analysis. So we have about 1,860 dots in each of these scatter plots, one for each stimulus. And we plotted each country against each other country. And you can see from this diagram that there is no obvious trend in favor of one or the other. However, this is in contrast to what is in the paper. This is a figure from the paper that shows US versus Japan. This is the same analysis, the plain MOS, Japan versus US. That has to be compared to the other one, which is the same graph, but only the axes are reversed. But you see this, our point cloud is right on the axis, while there's a clear tendency, a bias between US and Japanese data. All right, so then the statistical analysis was continued there. We thought, well, maybe if some of the points here, maybe we can make an analysis per point here, per image, and see whether there is a statistical difference, let's say between, again, Japan and US. So the null hypothesis was that the ratings from the two countries are from the same normal distribution with equal mean and variance, and then we performed a two-sample t-test to figure out whether there was a significant difference. And then on this horizontal line, for each image labeled 1 to 1,860, we plotted a little line up or down when at that image we found a significant difference at the 95% level using the t-test. And we can see that, okay, there are these significant or these images where we had a significant difference in the MOS. There's, you know, they're sort of randomly distributed depending on the countries involved, and they're also randomly up or down. The line would go up if the first country would have a larger MOS, and down if the other country would have a larger MOS. Okay, so here we cannot find any statistical or any indication that there is a difference, even looking closer at image by image. Okay, so then we took another look and plotted here in the histogram the ratings from the Netflix data set on the visual analog scale from 0 to 100. And you see that there are prominent peaks here. These peaks come from the design of SEMVIC, where in SEMVIC you have, these, this was the interface. The labels bad, poor, fair, good, and excellent are written on top, and also there are tick marks here, and the user selects a slider on each of these bars. And people read the labels and people see the tick marks and they act according to them, as you can see here. So there's, it's 50 here where the top is at fair, is at the label and at the word fair written above the scale. And likewise here. It's also interesting to see if people were not quite sure about whether this is poor or fair. Okay, then they attempted to vote in the middle here. So there was a little hump here, right in the middle between the large peaks. So this motivated us to convert the VAS scale to an ACR scale just by thresholding, at equal intervals according to the scales given there. And so now, all of a sudden, we have ACR data out of the Netflix data set, and we could then do the same analysis for thresholds as we've done it before for the other two larger data sets. So this is the result here. And this was a bit surprising that the intervals on the scale with the taus there came out to be almost equal. So also in this, from this analysis, we cannot see any difference between data sets from different countries. Also, the sigmas seem to be very, very close to each other. The lapse rate to turn out a little bit bigger here, about 5%. that's not alarming. That's when people do studies for psychometric curves, 5% lapse rate is common there. Okay, so there are hardly any significant differences in the thresholds, and that does not seem to be any indication of country-specific differences at all. Okay, so what are the limitations of this study and our future work? So first of all, the normalization in the models was done by fixing the first and the last thresholds to 1.5 and 4.5. And I realized too late that it would have been probably better to leave this open and also allow those to be country-specific, and then do the normalization by a different anchoring scheme. So z-scoring would be just a standard way of doing it. And then we would have also country-specific tau 1 and tau 2 and tau 4. So we will do this after, in the next weeks. Then the lapse rate was global. We could also have the lapse rate, made country specific, and that could even improve our models here. But in general, analysis of the benefits of including such a lapse rate in these Estonian models is still outstanding. That would also be an interesting piece of research, I think, independent of the country-specific question. Then the compute time was very large. So the MLE for 10,000, more than 10,000 parameters for conic 10K took 13 hours on a MacBook Pro using a MATLAB. And a reduction of runtime might be achieved when we lump all the images together in a single random effect. Well, I'd like to try this out to see what we will get there. Then also, besides country-specific models, we can have subject-specific models like the P913. We can add that also here, but this would increase the number of parameters substantially. And the binomial model regards the influence by images as a random effect, and only with one parameter, the sigma, and we can have a constant effect there also per image that we might want to consider. That would make the model more complicated, but maybe better. And lastly, the Netflix public data set is not consistent with the QMX paper. We should discuss this further. We don't know where the differences were created. One possibility would be that there are many more subjects that were mentioned in the paper, like 1,400, but there's only 10,000 in the data set. And the country-specific differences shown in the paper, they are not in the data set. So somewhere there was something lost on the way. So this is still unclear and certainly not final. Okay, the conclusions are that the hypothesis of significant differences in rating behavior is confirmed for some of the data sets at least. So the thresholds that we have that model the country-specific features, they are different. And also the likelihood for extreme ratings differs significantly between countries. But overall, a more detailed analysis should still be carried out. And the open questions with respect to the Netflix dataset should be settled. And so future IQA datasets can take this into account. And also when you reconstruct the scale values from data, that could be taken into the models. And lapse rates are interesting to study. So thank you very much for your attention. And here are some of our acknowledgements, or all of them actually. So we can discuss questions now if you have any.
Thank you very much. Yeah, we're waiting for questions. This is a very interesting topic. Any comment, question? Ali, please.
No, thanks for the extensive analysis. It was fun to follow through. I may have missed, so I want to first confirm if you had any details, if you mentioned any details about the translations of the questions or of the scales.
The questions were always the same in the data sets, Conic, 10K, and CADIT. They were in English. So
they were in English. Okay.
They were all in English. And the Netflix data set, they were not in they were adapted for two countries, the United States and India, it was English, and in the other two countries, it was translated. And it's in their paper, but I don't know what the words are. I don't know.
I see. Yeah, most of the time it's not a crucial issue, but I can see at least for some of the languages that I am aware here might be a little bit confusing if I directly translate it, but I'm sure there is a better qualified person to translate those at the time for the experiments. I was wondering if there is any other maybe studies that can also take this into account.
No, I'm not aware of it. Maybe Simon has an idea. He's also here, I think.
Yeah, I'm not aware of such either, but yeah, obviously how they understand the ratings must be important to how they use the ratings.
Yeah, I guess numerically it should be universal anyway, so it must not have a major impact. That's what I would assume too.
Yeah. There are some citations in the QMX paper from the Netflix authors where they point to some psychological findings in other areas. So it's an online page. You can look it up. It's I think number 18 or so. So maybe we can find some more indications, but it would not be for image quality, but for other things.
One more thing about this is that did you find any correspondence between the quality of let's say the bandwidth provided on average in the country versus the maybe the extreme rating probabilities or maybe the tolerance to lower qualities, etc. Did you find any bias that corresponds to internet service provider performances in the countries?
No, we only used two content providers, one for each data set, and Netflix had their own distribution channel. So we didn't contrast the two. Also, it would be difficult probably because we were using different methodologies, DCR in one and ACR in the other. It would also complicate it a little bit.
Sorry, I wasn't clear. I think what I meant was maybe the internet speed play a role on expectations of the users, and then rate that can maybe correlate to some of the ratings as a bias in the ratings maybe.
Okay, so the internet bandwidth. Okay, so this is the images were all preloaded, and so they came up immediately. And for video, I don't know how they did it there, but we also do studies for video, and we also upload them, preload all the videos of an experiment before the user can start to do the ratings, and then the internet speed would probably, hopefully not be relevant then anymore.
Yeah, I think not during the experiment, but what I meant was maybe previous experience, having a lower internet speed maybe make people in those corresponding countries with lower internet speed make them more tolerant towards lower video qualities, or give them an expectation of an lower quality, and that might result as a bias in the country's general quality evaluation.
No, that's an interesting question. So actually, we just ran another experiment on a different subject where we asked the participant, "What is your internet speed?" And so we could do an analysis on that. I will check with my researchers.
But yeah, more generally, to follow up on that, there could be many reasons beside merely language or culture. If one country has on average poorer or better screens, we can definitely not rule out that these things could influence what we are looking at here, at least not right now.
Okay, thank you very much.
Okay, Alex, please.
Yeah, I could probably retrieve it from the original data use. First of all, thank you very much, Dietmar. Very interesting work. Excellent. So I could probably retrieve it from the original data, but I'm not sure how were the verbal attributes versus numeric representations on the scale. So we're always, I mean, in the NIVD VAS, I saw that apparently there is a screenshot from your screenshot. There's no numerical label, but you have this kind of scale that is being shown, right, to subjects. So there's some kind of mapping involved in a way to some kind of linearity, right? How is it in the other two databases? Is it do you just have the labels, or do you really have the numbers? I mean, for this database, it's relatively clear, right? I was more referring to the other two. Thank you.
Yeah, in the conic data set, we had ACR categories. So we gave the words, not the numbers, from bad to poor to excellent. And in the other data set, it was the CADIT. It was a DCR. So the original was shown, the undistorted original, and then the distorted one next to that. And then it was DCR category, so not a visual analog scale. So the analysis, the primary analysis that we have here relies on ACR ratings. So we had to convert the Netflix data set to ACR to carry this out. And this slide shows it again. And the other were already on the discrete 5-level scale.
No, I was more interested. I understand. Thank you. I was more interested in whether additional numeric values were shown, right? I mean, there is this. I mean, there could be an assumption that people may be differently using the scale depending on whether they have some additional either graphical or numerical aid, right? I mean, across nations. So that the understanding of the labels doesn't play such a big role, but you're somehow, linearizing the results more or better, right? And you are not so much relying on the verbal effect, so to speak, right? Because the Jones-McManus paper you cited basically only had the labels, right? And if this is the same in your case, then it's very interesting, because then it's the labels primarily. And now it would be super interesting what happens if I have a bigger, let's say, graphical and or numerical support on the scales, right? Regardless of whether it's DCR or whatever, right? I mean, just this kind of mental aid of having some numericals or graphical representation, which I think in this case is given, right? I mean, if from this picture that you show, if that is the rating scale in the small box on the left of the plot, right?
Yes.
Then we see that there's this kind of graphical representation, which aids the user in kind of linearizing, so to speak, the results, right?
I think, that's an excellent topic and worth pursuing. So one conjecture about why we did not find cultural differences in the Netflix data set could be just this cause, right? Because that they have this scale there, and okay, they're ignoring the labels bad, poor, but they just go on the scale, and if the tick mark seems to be okay with them, they drop their pointer there. But here we have no country-specific differences that we could see in the 10,000 subjects at least that we have in the data set. And that could be the reason why these country-specific differences disappeared. And that would be good. And that would be an argument in favor of using the visual analog scale over the ACR scale. Earlier this morning, the ITU was discussing this question, and it was decided to go with the ACR scale. Well, I have my doubts whether this is really the best way. My personal preference, and this is what we're doing in JPEG AIC now, is to have an interval scale going from 0 to 100 without any tick marks and without any labels, except at the answer labeled, the most extreme, completely bad or super excellent or not the best imaginable. And then, it is more like a perceptual task to place a pointer on this interval rather than an intellectual saying, okay, this is poor or this is good or bad. That would be my guess, maybe, or my hope that that would be very good if we could show this sometime.
I fully agree. Just to to add to this, I think it would be very interesting also to look a bit more in detail what previous authors have done when they say they have used the ACR scale, right? I mean, sometimes people do use the ACR scale, but still put numerical labels in addition, because there are also different variants, but that would be super interesting, right? So maybe a task which we could do together also with a few other authors to look at what do different studies do, right? And can we retrieve such information from that? Thank you very much again. So
yes, so Simon would probably jump in now and say, okay, he would suggest that in all papers we should publish not only the numbers, but also the interfaces that show exactly what the subjects will see. Right, Simon?
Yes, pretty much. And I have tried to look a little bit into what different experiments are using, and often you just see, right, that people write, we use the ACR, but I don't really know at all. Did they use numbers? Did they use words? Did they use something else? Because I feel you're often left guessing a little bit what has been done in such experiments.
Yeah. Couldn't agree more. Lucas, please.
Yeah, first of all, let me just echo everybody else. This is a fantastic analysis. I hope all the papers could be analyzed in this, really rigorous way. And thank you so much for that. I also want to thank Alex and Ali for the interesting conversations about the scale, because that is something that we have, even designing this study, we have been going back and forth about where do we put the labels? Do we put a number there? What is more biasing people or what is less biasing? So at the end that we have fewer, let's say, fewer differences between the countries, it was actually something that we wanted. We didn't really want to make it completely agnostic to the number and making it, because we don't understand some of the languages, so it's easier for us to have something more let's say uniform, but it is totally we may not be measuring what we think we are measuring in terms of the labels, right? Because if we read too much into the labels saying like, oh yeah, people think this is bad, this is poor, I do believe, and that's also tying it back to the previous talk when we are looking at the expert scale. Like people most likely just sort of try to make a mental model that is spreading the data set into this, these are bad, these are excellent, and something in between. We actually did try a pretest where we removed the 5 labels, we only had the extreme labels. And the behavior was similar to this one, if I remember correctly, but the mountains were much lower. So it was more like a, as you would filter out the tops. And it is more that people still do sort of break it into intervals, even if they do not have that explicitly. And they say, oh, this one is better than that one, and I've seen already that one that was worse. So they try to sort of bisect the whole thing, I would say. So it's this is also like what is more mentally simple to the subject, right? So I think all the studies in this have been really interesting, and I don't think we have a clear answer to what is the best thing. And I am 100% for, yeah, let's just report what we've done exactly. Did we put numbers? Did we not? Because one thing, sorry, I'm just blabbering, but there's also where you put the default is different for the slider. We had one study where we had a slider in between. We started on 50%, and then this was hands down the highest frequency of occurrence. People just would say, oh yeah, this is somehow fair, so I'm not going to move it. And so in this one, actually, we removed it completely and they had to click first. But yeah, all these things have impact. That's probably in a nutshell what I'm trying to say.
Okay,
Yeah,
thank you very much.
Okay, in the interest of time, I don't want to comment.
Well, no,
No, I was just mentioning regarding the slider and the position of the prompt to the user. There was a paper by Ulf Reips from the University of Konstanz with a psychologist with whom we collaborate, and they did research on this some 5 years ago, and that's also their recommendation. When you cannot remove or you should try not to give a default position for the selection. Just let the user choose it himself or herself. I tried all the different options and analyzed it.
Yeah, I'm really, I would have like thousands of comments and love this discussion, but because of being a chair, I cannot do it. We have to go for the rest of the presentations. But think about the future of the SAM. I find this as very, very interesting topic for like focusing on the scale analysis, which is longer within VQEG than I am. So it's really long discussion, but still not a clear like kind of explanation or conclusion. Okay, so we have to go for the next presentation, cut this discussion, but still staying with different experiment precision measures. And this is Alex's presentation and remote testing of high resolution image and videos, very much related.
Yeah, you need to unshare your slides because I cannot share at the moment. Please. Ah, super, thank you. Yeah, now it works. Do you see it? Yeah.
Yes.
I'm unfortunately a bit tight on time because I have some urgent stuff that I need to do afterwards. So I will only follow like acoustically for the remaining 2 talks already in prior. Some apology for this. Okay, so let's also try to keep this relatively brief. Probably some people know this already. So I'm summarizing work that primarily Rakesh and Steve did from our team. So bear with me. I cannot probably answer all of the detailed questions you may have. So yeah, but of course, you know the tools mostly. I think you know them, and you can of course refer to them as well. So yeah, what was the idea? So lab studies obviously are time-consuming and expensive, and sometimes you cannot run lab tests. And we have seen, of course, the great crowd test that from the previous presentation. Now we were interested in seeing how does this work for high-quality video and high-quality or larger images, high-resolution images. Yeah, and so we were considering how can you do this when you don't really know what the screen size of the subjects will be, and how can you still run meaningful tests in such a context without actually lowering or adapting the resolution of what is being shown if the original resolution is higher. And so this is due to the challenge that the hardware that's being used is not really controllable, and there also may be impacts due to other context aspects. Can you see my pointer as well? I hope so, right? Yeah, most likely.
Yeah, it's correct.
Okay, and then so the idea would be to display some sort of crops. I mean, crop of the respective image or video, and this would be an alternative to playing lossless versions of video, right? So you don't have any impact of this. So the proposed approach is here indicated for images and video. So in images, use different patches, and video use a predefined center crop of losslessly upscaled video, and then basically you have you're basically invariant to the display that is being used. We refer to this. That's actually from the tradition of where this comes from. This is the work in Q14 on peanuts. We have referred to such sequences as AVPVSs, meaning that in essence, this is really what you show to the subject. So if you don't really have things like stalling or the like, it doesn't make such a big difference. But if you have such things in addition, then it makes sense to really refer to this in a different way than to what is actually being used before the upscaling and or further processing. Okay, quickly for the high resolution images. So here we took a relatively pragmatic approach. We used 39 UHD1 4K frames extracted from UHD1 4K videos, cropped here to quadratic form 2160 by 2160 for different genres. And then we did a 1-pass HEVC CRF encoding chosen due to its link with the underlying image coding standard. And knowing that it typically outperforms JPEG in most cases. And so we get a result of 371 images encoded with H.265 and and then we use classic ACR. It's actually now very interesting after our discussion. I should really look into more in depth how exactly the scale was presented. I don't have it here on my slides. If I had a few more hours, I would have added it. Anyway, so we had a corresponding lab study where the full square images were shown with 21 participants. And then we had a crowdsourcing test, and here we had the original images sampled into 4 1080 by 1080 images with 15 minutes duration, and then a pre-test questionnaire, classical things like age range, self-judged visual acuity on an ACR scale. Of course, in a crowdsourcing context, you could also do it otherwise, but here we were just doing it like this. Very relevant, of course, for the intra-subject differences, especially when you don't have other means for really testing it. It's a whole topic of its own, obviously. Then what type of device is being used? This can also somehow be extracted from metadata and be double-checked. And then test environment information. This could essentially also, if you had a webcam, be analyzed, but of course that's very invasive, so we didn't do that. So we asked people, are you alone in a quiet room, some noise and distractions or significant noise and distractions? And then from these 1,484 patches, participants rated 150 randomly selected ones. There was no training phase, so training happened basically within the test. And the crowdsourcing results, most participants voted for less distractions from these 3 categories here of test environment. And the majority of test subjects were in the range of 18 to 39 years. The total was 38 participants. And in this case, it was not like using a crowdsourcing platform. We recruited them via the university mailing lists. And we had an average of 17 ratings per each of the patches. Here you see the MOS distributions in MOS bins. And we can see that in the crowd test, the participants, so we see lab left and crowd on the right. And we see, so it's always like in the header. Sometimes it's not, oh no, it is here on the left hand, it says lab, but it doesn't say crowd here. So that's how this formed, and we see that the participants in the crowd context are a bit more critical. Yeah, then if you do just a pure comparison here in terms of correlation, then you see that the correlation or also RMSE, etc., are quite high correlation, relatively low differences obtained. But you see also a bit similar as we have seen previously. You see a slight curvature. And you see that on the mid-range, the subjects seem to be rating a little bit lower on those patches in the crowd test than they would in the lab test, right? And the extreme points, it's then a bit more agreeing again. Here's the lab versus crowd comparison in terms of this Hosfeld et al. SOS analysis. You see, obviously, you see based on the lower number of data points, you see that this kind of sampling here in the case of the lab test, and here we have more data points, obviously, for the crowd test. Please note that there is a difference here in standard deviation ranges. So here it's not scaled to the exact same range, and there is this A parameter that is in this sort of quadratic approximation approach here in this Hosfeld paper. It's cited on a different slide. I have forgotten to add it here. So the reference is there, but not on this slide. So you see that this A value is lower here and higher here. So the differences across subject is a bit higher in the crowd test, which is of course corresponding to expectations also. Now, short-term video quality assessment. Here we are comparing with a data set which is already publicly available, which is in Rao et al. 2019. the AVT VQDB UHD1 data set. And from that, for the crowd test, for the comparison, we used 540p center crops. That's really a very low resolution if you consider the high resolution in the original data set. And then we ran a lab test for comparison. So 6 different videos. So the lab test in comparison is actually already available, obviously. And then the codecs used are from the Peanuts phase 2 competition, H264, H265, BP9. That's where this data set also comes from, from the Peanuts phase 2 context. It was not content used there, but complementary to partly at least. Yeah, and then the encoding resolutions are between 360p and 2160p. And then the total number of PVSs is 180. Here, 29 test subjects in the lab test. And yeah, so there were no outliers in the lab test, which was the condition in the Peanuts phase 2. So we applied that also for our lab test. As I said, the lab test is already a bit older, and now the crowd test is what was new in this publication, which appeared in 2023 in the QEG journal. Yeah, so we used AV-Rate Voyager for this. That's basically our open source approach for subjective tests. It would be also quite nice to discuss this further with the colleagues from Netflix. Maybe some ideas can be considered jointly there. So in any way, so subject recruitment primarily from the university body, over 90%, again by email lists, and some were recruited from people known to the authors. And test duration for the crowd part was about 15 minutes. There was a pre-test questionnaire, then age range, and then visual acuity, what device type used, same or similar to the image test. And then again, test environment, same as in the image test, 3 options. And then we checked basically from metadata that the device resolution was at least 720p, so that the 540p crop was obviously viewable correspondingly on that screen. And each participant rated 30 PVSs randomly selected out of the 180 PVSs. And again, in this crowd part, there was no training phase. And again, similar to the image test, less distractions was the average rated here. Let me, yes, same middle category, so to speak. Exactly, and then age range again similar to the previous test. Yeah, and around 18% of the subjects had a resolution of full HD or higher only. That's relatively low. 175 participants in this crowd test, 19 outliers. We used the same 0.75 criterion as used in the lab test. Based on person correlation. That's the same approach that we used in the ITU competition for Peanuts phase 2. And the average ratings per PVS was 22.15. Again, the crowd tests are more critical, the crowd participants. So you see here on the left-hand side the lab test, and on the right-hand side the crowd tests. And from the distribution, you see that there are quite a few more lower ratings, especially than in the lab test. And in terms of correlation, it's again relatively high, which is remarkable considering that we used only a center crop in the crowd test, whereas we used the full resolution, obviously, in the lab test. That's actually quite interesting, we find. And also in terms of errors between the two, it's relatively low. And now in terms of this SOS analysis, you see that they are almost the same, right? So very similar A values here, A 0.24 and 0.49. That's 249, and so that's very similar. Yeah, and then we had another lab test available from the Peanuts context that was for the long database that was published in QMX this year. It's the Peanuts UHD1 long. So, and here for the crowd test, we used a 720p center crop, which is really a bit awkward, we must admit, right? Because you're now watching a longer sequence. in this very small resolution, that means that it's a crop actually. So you don't see the full content, right? So you would probably not perfectly understand the sequence if you were looking at it, but okay, it's only about quality rating, so why not? Stalling is included here, and also quality switching, right? Again, 30 different videos, each 2 minute long. Original resolution is UHD1. Codecs used, the ones that were previously mentioned. So it was again from the Peanuts Phase 2 competition context. Encoding resolutions 360p up to 2160p. Yeah, and as I said, initial buffering, stalling, quality switching as additional degradations. 30 PVSs and lab test 31 participants, and yeah, which is the criterion for the database, 0 outliers with this PCC criterion larger than 0.75. Then for the crowd test, again, AV-Rate Voyager, now 15 minutes test duration, because we, 5 PVSs were randomly selected out of the 30 PVSs. Here there was a short training phase with 1 video showcasing all impairments. Oh, funny, it's a LaTeX error here. That should be a real error. Sorry about that. So it's the same questionnaires as in the short video test as shown earlier. Now the test subjects were recruited really via click workers, so it's a real crowd test in quotation marks, right? So 100 participants, and most participants again were judging to be in a less distractions environment. Smaller than 10% of the subjects in this case had a resolution of full HD or higher, but we checked, of course, that the resolution, considering the 540p, the center crop, we were checking that the resolution was appropriate. And the average ratings per PVS were, in this case, 17.2. Again, the test subjects in the crowd test more critical than in the lab test. As said, which came in all cases to a little bit of a surprise to us. Impressively, though, I mean, subjects really could not really view the content in the same way as in the lab test, where actually they had the full resolution available. Again, pretty high correspondence, and that even for the case that there were stallings involved, right, with a little bit higher deviations when actually there were 0 stalls, right? So when stalling happened, there are very few cases only, right? So there are only these very few green points here, which are the 2 stalls, number of stalling events, that means, right? Because it was 2-minute sequences. We may hypothesize that when stalling occurs, that is kind of normalizing the results, right? You're not paying attention to the video aspects anymore. Whereas if there are 0 stalls, then video quality plays a bigger role, right? And then there are some bigger differences between crowd and lab. Okay, and in terms of this source analysis, and here's the reference. So also I will upload the slides tomorrow, or provide them. You see that there's a very similar A value for this analysis, so indicating that there's a pretty high correspondence between the 2 tests also in this regard. Okay, conclusion. So it's a proposed method that can be used even for high resolution systematic video and image quality tests. Seems to be working relatively well, even for non kind of saliency based patches, which I forgot to mention. I have that on one of the earlier slides, that could be done, of course, but really a center crop in case of the video. And there's a relatively good correlation between lab and crowd tests and the relatively high PCC and similar SOS parameter values. And all data is made publicly available. And then come the references, and you can check that out when I upload the slides or provide the slides tomorrow. Thank you very much for your attention.
Thank you very much. Are there any questions? Lucas, please.
Yeah, thanks, Alex, for the presentation. It's pretty fascinating that the results are so well aligned. I'm just wondering, have you considered also running just the crops in the lab as well? Because right now I feel like there are 2 moving parts. One is the crowdsourcing versus the lab, and one is this crop. I would really like to understand, if in the lab you get basically the same thing.
Yeah, you're absolutely right, and we are discussing this. So yeah, it's a topic we will do. We have some student projects running. It's a very valid question. Yeah.
Yetma, please.
Yeah, thanks, Alex, for the interesting presentation. Yeah, high resolution is very challenging, and we have also been thinking about it. Already had a paper in it at QMX 2015 that you may remember. And now my question was, I think the push for this should be that you can make these tests in the crowd and then collect the ratings for the different patches and merge them for an estimate of the quality of the full scale, the full resolution video. So for this, did you run any experiments with that respect yet? So in the lab, you have the full resolution on a large screen, and then you compare it with the processed results from a crowd that has seen only crops. And then the questions are like, well, how do you select the crops and how big should the crops be, etc. I think that would be really good to have a methodology that's tested and shown to work in this way so that we can use crowdsourcing using crops for the estimation of very high resolution video at home or in the lab.
Yes. Yeah, I mean, this is, of course, the idea, but we have not basically varied the crops. I mean, there's one study from Steve Goering where we have actually varied the crop, right? It is also cited in this QEG paper. So there we did systematically evaluate, and you see, I mean, the smaller, for example, you make the crops, then the worst gets the correlation, obviously, which is a bit expected. But we have not played, for example, with which would be also an approach model-based saliency, right? So that you beforehand select which area would you likely be cropping, right? For example, you could assume that the center crop actually works well because you can assume that mostly relatively contrasty and also high frequency content components are quite likely to appear in the middle, right? Just statistically, right? So it's relatively unlikely that for the test sequences we're using, I mean, mostly we're not really using cinematographic content, where obviously if you then take a center crop, you may be completely off because the key subjects may be at the side of your scene, right? But in these typical quality test material, you can assume that the kind of high frequency, I mean, high spatial frequency, that is obviously, and contrasty parts of the content will quite likely appear also in the middle of the frame, right? Which probably makes it understandable why the center crop kind of works. But obviously it's not like a pre-selection or something, if I understand you correctly, which part of that video would be the best one to choose, and then can you maybe automate it so that for that particular sequence you have the optimal crop that you then present in the crowd. Well, it's very interesting. We have discussed it several times in the group, and but we have yet not conducted such a study in detail.
Yeah. And now the questions. Yeah, seeing Naga, I will add just my comment. So first of all, Lucas, I don't see why we need a lab test again, because the moment you see a crowdsource very similar to lab, it means that in the lab it should be just more similar. It shouldn't be very different. Yeah, that would be very surprising for me. Like we add 2 levels of distortion, let's say, yeah, and there is no distortion. So one level of distortion should be even less. But in my opinion, like my personal opinion, like feeling, seeing those results is that we are definitely not doing quality of experience tests. This is pure pixel quality, yeah? And we probably should name them like that, like very honestly. Like the moment you can crop the stuff and still the results are so similar, people clearly don't care about what we are showing them. And they probably care what we are showing the moment that they show something else. Yeah, but very interesting for sure, and a lot of more research is needed here. Yes, Lucas, please.
Just a quick reaction from what the presentation was about. I believe that it's not a typical crowdsourcing as we understand it as well, and that is something we have done over the corona, is that we were able to run a test that was outside of the lab, but with trusted observers, and we got almost the same thing. So I do agree with you that this does seem that it's not. I just really want to have a powerful message of saying, oh, you can do the cropping and you still get a valid results. Just so even when it's separated, because here I'm not sure. Maybe it's just overcompensating, like one thing over the other. Who knows? So I just felt like it would be more clear to have this, like everything else is fixed and you only vary one thing.
Yeah, it's always do step by step. You're right. Okay, thank you very much. Well, just to be
okay, I need to leave. Sorry about this, but I'm listening in via mobile. See you tomorrow. Bye-bye. Sorry about that.
Thank you. See you tomorrow. Since we run out of time, I have to ask. I have to ask Shell. Can we continue? Which is probably better idea than move some session somewhere.
So how much is left?
2 presentations.
Because I think we planned for like a half an hour overflow time, but I don't think we should go any later. But if everyone wants to go on, then we can of course do that.
Yeah, so maybe my question as the chair of the session is that if someone prefer to move the session because really wants to hear the presentations, but then please let us know in the chat or something like that. If not, then we will just continue to keep it all together. Yeah, I guess that there are some people that really wanted to connect to some and maybe not so much interested in other sessions, and then they prefer not to connect like tomorrow or the day after tomorrow. Okay, so now we've got Dominic again from TU Ilmenau, and this time we compare 8K HDR video. Please go ahead.
Right, thank you very much. Can you guys hear me?
Yes, perfectly clear, and we can see your slides as well.
Wonderful, thank you very much. Yes, that is a very good time actually to talk about what I'm about to talk. It is the effect of viewing distances on 4K and 8K HDR video quality perception. The talk today is basically based on a paper that we just recently published and presented, and a little bit additions from another paper we did earlier the year. Right, what is the motivation behind it? The 8K content that is actually being produced or has been produced over the last couple of years is now increasingly available. However, the benefits of the 8K resolution itself compared to 4K are still quite unclear and debated. Generally, you can say that the viewing distance is crucial for video quality and higher resolution especially. The optimal viewing distance, according to the standards/recommendations, balances factors like resolution, pixel density, screen size, and preferences. What we also know is that video quality models use usually the optimum viewing distance and screen size as factors to calculate their quality scores. Some related work. I'll skip the first 2 parts because I learned just today that is all known. There's a paper that states that if people sit at suboptimal viewing distances, the differences between resolutions cannot really be detected anymore. Suboptimal meaning larger than or further away than planned. There's another, or in the same study, actually, they found that 82% of owners of UHD TVs do not actually sit at the respective optimal viewing distance. And we found also in a paper that we published 2019 that a temporal switching methodology is quite suited to make people see differences between UHD 1 and at that time Full HD content. Right, there's another paper from 2015, that is the latest one that I found, that looked into what are the actual viewing distances in people's homes. In 2015, the median viewing distance was at 5.5 H. They also asked people if you were to buy a TV / change your living room, what would then your replacement viewing distance would be, and that is mostly because the screen size increased 4.5H. We also did a small preliminary viewing distance study in 2022 and found that people roughly sit at 4.7H. If we now compare that to the optimal viewing distances as announced in BT 500 and other recommendations, you see, even for full HD 2K, the optimal viewing distance is way closer than the actual median/used viewing distances. And we therefore wanted to see, does it even make sense? And that is not only the only research question that we wanted to see or check out is like, how is the UHD video quality being affected by the various viewing distances? And yes, as a video quality, I think we just had an interesting point about video quality and quality of experience. I think in this study, we look into video quality. Second question, are subjective 8K video quality tests affected by training effects? Also an interesting point being raised already. We have maybe a little insight into that. Third research question, what is the preferred viewing distance for 8K viewing situations? And the fourth one, is it worth watching 8K content in a living room scenario? Right, want to directly jump into our experiment. We did a test with 8K and 4K stimuli. I will only talk about the 8K for the moment and come back to the 4K later. All 9 8K HDR sources with varying SI complexity, so spatial complexity. You can see that they're color-coded from high spatial complexity to low red to green. We used 10-bit subsampling 420, transfer function BT 2020. Frame rate were either 30 or 60 frames. And for encoding, we used H265 CRF12 for playout reasons. And the stimuli were 2 times 8 seconds. So we had stimulus was 8 seconds. We just repeated it once. Our setup, we used test rooms according to the recommendations BT 500 and P910. An 86 inches LG 8K screen was used. So screen height was 1.07 meters. And we also used 7 viewing distances ranging from 0.5H to 3.0H. We used a random order of viewing distance. So people had, like, not everyone started at the same, but at different ones and then moved it randomly. We had a paired temporal switching comparison and quality rating, meaning we had a stimulus that was switching between qualities every 2 seconds. As you can see on the right-hand side, it was color-coded in red and blue. And after the 16 seconds, 2 times 8, we asked for a quality rating. Which version of the sequence did you perceive as better? The scale rated ranged from red is better, via red is slightly better, to none is better, and the same with blue. Before and after the study, we asked subjects to select their preferred viewing distance for that screen while we turned on an 8K movie so that they could place themselves at the preferred distance. We had 2 different comparisons. First, starting with the first one. As I said, we had these 9 8K stimuli and we downscaled them using a Lantroche algorithm to 4K. And then re-upscaled that 4K to 8K again using nearest neighbor algorithm. So as if someone has a 4K screen, we played out that on the 8K screen. These are the results for this first comparison. We had 27 valid subjects, median age 26, so quite young people, have that in mind for later. And we recalculated the rating so that positive values ranging from 0 to 2 prefer the 8K and later the enhanced 4K, but for the moment prefer 8K. So not red-blue anymore, but positive values are 8K are better. What you can see here are the different 9 clips and the relative distances from 0.5 to 3H. And what you can see is the closer the viewing distance are, there's a higher chance for people to distinguish between 4K and 8K / say that 8K is up to slightly better. To have that a little bit more ordered and a little bit more understandable, we put the 9 stimuli into 3 SI groups ranging from high to low. And what you can see here is that the SI clearly has an influence on if a stimulus can be distinguished, if a stimulus is in some way 8K ready or not. And what is also visible that like starting from 2H, it is not really possible anymore to distinguish between 4K and 8K, even for the stimuli of high SI. I told you we had a median age of 26 of the participants, and that's why this slide might not be too, like not telling too much, because we also looked into people's eye acuity. And the threshold was basically 1.57 that we group people into the high and low acuity group. However, what you should know is that 1.0 is actually the normal vision that people say, the 20/20 vision. So even people in the low acuity group still had, compared to the rest of society, quite high or quite good vision. And therefore, also we could not really distinguish between people's acuity when it comes to quality ratings. One quick look into the earlier study that we published. We were talking, or you were talking about like memory effects and repeating scenes and repeating contents like in the same test. Actually, we did an earlier study where we had everyone that participated in our test start with the 0.8, the orange marked viewing distance first, to see if that training effect in some way plays a role. And what you can see here is that the other distances had an average of 3.5 occurrences of the same stimulus. For 0.8, it was always the first time, and it made it harder for people to distinguish between 8K and 4K, and that way the 8K was also not really rated as slightly better in that regard. Right. And to compare the two studies, study 1 is the one from that earlier study, study 2 is the one from the current study that I'm basically presenting, is that they are quite well in line. You can see the closer you are, or the closer people sit, the easier they can distinguish between 8K and 4K, and the better actually 8K, or the more 8K can shine in that regard. If you sit very closely, 8K makes sense. The further you sit away, the less of a difference it makes actually compared to 4K. Told you we had a second experiment with 4K, right? And we had these 5 other 4K stimuli that we used. We wanted to see, does it make sense to use a good 4K upscaling algorithm to 8K compared to that native 4K that we used also in the other comparison. So the good 4K upscaling was a Lanczos-based algorithm. I know they're way better at the moment, and you can use machine learning and all the magic things. We wanted to go for a standard but still good algorithm, and compared enhanced 4K, 4K plus, with native 4K. And that showed us, compared to the native comparison that you can see in orange. So orange are the original 8K versus 4K, and blue are the enhanced 4K versus native 4K, that there is a slight increase also for closer distances. So if you sit very close at the screen, it also makes sense to upscale your 4K stimuli to 8K nevertheless. But it is not as great as if you had original 8K content. The last thing that we looked into was actually the preferred viewing distance. Told you we asked people before and after for their preferred viewing distance. And you should also remember that the average viewing distance in living room scenarios is greater than 4.5H, at least in that 2015 study. And also have in mind that we could show that 8K improving the video quality only for distance up to 2H. People or subjects' preferred viewing distance, or average preferred viewing distance, was roughly at 2.1H. That is resulting in a vertical viewing angle of roughly 45 degrees and resulting usage of the field of view of 18%. and there was no significant difference between asking them before or after the study. To conclude that, we could see that there's a strong influence of the viewing distance of video quality, especially for UHD resolutions. 8K seems to only profit over 4K for close distances of up to 2H and complex or spatially complex videos. When content is being repeated, training effects are visible. So people actually do look at this respective pixels and find their spots where to actually differentiate them, which is in some way not really quality of experience, rather it's rather video quality then. Realistic living room scenario would decrease the usefulness of 8K even further. The preferred viewing distance for 8K video exceeds the range where the benefits of 8K are actually visible. However, it is still closer than most living room scenarios. So if people given the chance, they still probably would like to sit closer to the screen. But obviously, it's also not only the screen, but also effects like the room and the room geometrics and lighting and other factors. At close distance, Alonso's upscaling for 4K might be useful. In the future, what we already have done is two other studies where we looked into encoded videos, so taking actual encodings into play, or non-repetitive content, so not repeating the same contents at different viewing distances. Also would like to look into JNDs and acceptability distance, and would like to have that data be included into models so that we can also see the actual scores when people sit at non-optimal distances. With that being said, thank you very much for your interest. Looking forward for your questions. If you want to exchange or if you want to contact me, please feel free to contact me via that QR code or the email address. Thank you very much.
Thank you very much for an interesting talk. Do we have any questions? Please, Margaret.
Hi, thank you for this interesting analysis. I'm curious, you said that your subjects had better vision than the typical person. How much do you think your results would change if you loosened control of the visual acuity of your subjects?
That's a very good question. I mean, I can only speculate because we only had that people with good vision. I would guess the results would even be less, like people would even find it harder to differentiate between 4K and 8K. The advantage of 8K beyond 4K goes away. The less of the older people get in some way, but also the worse people's eyes will be getting. Yeah, that is my assumption. So 8K might only be a thing for people with very good vision.
Okay, thank you.
Also, what is interesting, what I haven't talked about, I mean, especially when you get older, it's really hard to focus in close distances. And the closer to sit at the closer you sit at a screen, the harder it will then get to focus actually on the screen. So that is a factor that we also haven't really included into that yet. Of course, we had the young people.
Okay, Adi, please.
Yes, thank you very much for a very interesting talk. So I see that you had very nice analysis on the spatial complexity, but I'm wondering why you ignored the temporal complexity analysis here.
We didn't really ignore it. I ignored it for today's talk. Yes, we just did not find real significant differences. So temporal complexity didn't, at least in our test, didn't play a huge role. What I also should mention is that the variation of the temporal complexity in our test was not as great yet. So we're also always looking for new content. Our contents that we used just didn't have a lot of variation in temporal complexity.
Thank you.
Yeah, Lucas, please.
Yeah, thank you so much. This was a really nice, concise talk, and the messaging is pretty clear. Thank you for that. I'm mostly wondering, you used 8K HDR. Can you tell us a little bit more about the setup that you used in order to make sure that there are no frame drops? And
Sure. That is why we actually used, wait, I think I placed it here, H.265 CRF12. So we put a lot of effort into making sure everything was running smoothly and well. We had the latest and greatest graphics card, CPU, storage, and HDMI cable and TV. So we made sure there were no frame drops and everything was running as smoothly as possible. That came with the downside of CRF12. So we could not really play out like lossless video as we actually intended. But we said that CRF12 is still good enough to call it as close as losses as like one would get. Maybe in the future we would like to go even lower, and additionally higher in CRF to come to like more real streaming scenarios or viewing scenarios.
Yeah, and was it from a laptop, or how did you feed it?
We fed it from a tall computer, from a computer with a lot of like I can't tell you right now which one exactly it was, but we used a proper computer with a graphics card output.
And is the detail about the setup in a paper, or?
Yes, it is. It is.
Okay, fantastic. Thank you.
Thank you very much, especially that it seems that we should like understand that VMAF 80 is something that people will see as 90 in their homes, yeah? According to at least 90, yeah? This is interesting. I remember I had long time ago this discussion with Bob, and he said that this is pretty ridiculous that our metrics are not taking into account the distance to the screen, which definitely has an influence. Thank you very much. Yeah. Thank you very much for this research and talk. And we've got Andreas and Pierre. I'm not sure who will. Andrea. Okay.
I think I will start, and if there is too difficult question, Pierre will handle it, I think.
Okay. Thank you very much. So please go.
Okay. So I'm sure. Yeah, okay. Right. So the work that we want to present in this session is the recent work we did to compare different conditions for omnidirectional video with spatial audio. And we want to analyze that in terms of subjective quality and also impact on objective metric resolving power. So as an introduction, the motivation behind this work is that there is not many work on 360 video with higher order ambisonic spatial audio. And what we wanted to do as well is to reproduce a previous work that we did in collaboration with people from DTU in Denmark that did a 360 video audiovisual quality assessment, but with expert viewer. And we wanted to reproduce that in our lab with naive assessor and compare the data and the quality of the data that we obtained from this experiment. And moreover, what we wanted also to start to check is also for the quality of experience perception viewpoint, we wanted to showcase maybe effect also of what we call a reference and a consumer grade audio setup. So we will detail that in the next few slides. And additional motivation of this work are also what we wanted to conduct is a study on the experimental effort cost, so a little bit related to what we presented in the last talk in the SAM session, and also its relation with discriminability. And we wanted also to study the metric resolving power and its relation also with this discriminability score. And as well, what we propose is a method to apply no reference parametric-based audiovisual quality assessment model from ITUT P1203 mod 0 to 360 audio visual content with spatial audio. And we wanted to target this kind of metrics since they are lightweight, and we are trying to target more greener metric compared to VMAF or even more complex metric. So about the QoE condition, about this reference between consumer versus consumer grade setup. So on the left, what you have is the reference playback setup that we had in the previous experiment, and it was composed of ODC plus HMD and 26 channel Gen Lake loudspeaker for high quality pristine playback of audio file. So as you can see, people are sitting in the center of the room, and this spot is the listening sweet spot where the rendering of the 26 channel loudspeaker is optimal, and people were able to rotate on their chair on 360 degree to explore the content display in the HMD. And on the other side, you have the consumer grade setup that we produce in our lab, and that time was with HTC Vive Pro I HMD. It has a similar characteristic in terms of resolution pixel per degree on the display screen in the HMD. And also what we use for the audio playback was the built-in headphone. And this will be more like a consumer grade, what you can have in-house. And when you could consume this kind of content compared to this reference setup that not many people will have to visualize and display 360 audiovisual stimuli. So more about this ambisonic audio playback. So in our case, we had fourth order ambisonic audio file. So fourth order ambisonic file has 25 channels that capture different direction of the sound. So each order of the ambisonic will add more direction and more targeted direction of the sound. And this audio file were decoded with all-round ambisonic algorithm for the loudspeaker playback in the reference setup. And for the binaural rendering, we used Sparta and integrated into Reaper to have the rendering of this binaural sound using real-time messaging about the yaw, pitch, and roll of the HMD to play back and to render the fourth order ambisonic. So after, what we did as well is that for the first experiment, a lot of in the previous work that we did, a lot of SRCs were evaluated. 16 sequences were subjectively evaluated, but the database that we propose had in total 30 SRCs that could be evaluated. And for this new experiment, we couldn't afford even to annotate the 16 sequences. So what we did is to try to characterize the content. And there I will present how we characterize the video part of the content. So what we did is we compute SI, TI on the ERP, so equi-rectangular projection of the 360 content. And what we have here is the scatter plot with in red the sequences that were evaluated in previous work, and in blue the other content that were not evaluated but still provided in the database. And then I also included more recent work of this QoE Wave database that is just a database. I think for now there is no subjective score provided, and they provide, I think, 60 sequences of 1 minute long of 360 content with spatial audio with spatial audio. And what we can see is that the sequences that were evaluated in the first experiment cover most of the SITI space that is available from all the video that we have in that format. And then what was also interesting, since we are working with audio, it was also to try to characterize this audio part. So what we did is to use the zero crossing rate and spectral contrast computed in the first order, the zero order of the audio file, so this W channel. So if I come back there, it will correspond to this first channel of the audio file. So zero crossing rate is just a simple computation of how many times a signal is crossing the zero value. And in the literature and more on the audio side is used to translate the smoothness of a signal and also to characterize, for instance, audio voice quality. So maybe some good recording of voice will have a really smooth and really low ZRC score. But for instance, communication through a bad quality, I don't know, equipment like phone or something like that will have a higher zero crossing rate that will translate non-smooth signal. And the second characteristic that we choose was the spectral contrast, and it's a measure between the energy difference between the spectral peak and valley of a different subband. So in that example, there you have the spectrogram of audio file, and you have the different frequency that are displayed on the y-axis. And basically the spectral contrast computation is just taking some different subband and computing the energy of the highest part of the subband compared to the lowest part. So as you can see here, there is really, how to say, really high score for spectral contrast over here, since there is not many frequencies provided, and all the subband is at really low energy. And for other subband, you will have more contrast. And usually this in the original paper, this measure was also to try to classify different music instruments, since this statistic will translate some clarity of signal and per different subband. So similarly to SITI, we can characterize also the audio part with this two indicator. And again, there I represented in the red the sequences that were evaluated in the previous QE experiment. In blue, the one that were not evaluated, and this QE wave dataset in green. And to give you some example about what I just said before, these 2 points, for instance, are river stream. And so river stream is a recording of in a forest of a river stream that is passing along the camera, and the air drying is someone using air dryer in a hotel room. As you can see, the zero crossing rate is quite high. So this kind of audio signal are not smooth at all, since there is a lot of noise and maybe high frequencies. And this spectral contrast is also quite low, since a lot of frequencies are present and a lot of noise maybe coming from the natural surrounding, I don't know, wind, water, or this kind of thing, could characterize this river stream sequence. And on the other side, you will have, for instance, door open, chamber music, or car with chat. door open and car with chat are discussion happening inside the car and inside a closed room between different people. And the chamber music is a sequence where some people are playing on a stage in acoustic chamber, some music, and you can see that in that case the spectral contrast is really high. It's a really clear sound, not a lot of noise, and I think this can characterize quite well the different audio sequence that we have. So there I just provided a screenshot of the different ERP of the evaluated sequence to showcase the diversity of the scenes, like outdoor, indoor, with close environment or really large indoor environment. And after you have this air drying also scene with really loud air drying and a lot of noise, or this river stream over there, and more quiet room like this people playing music, or someone typing with typing machine outside and not speaking at all. So for the experience that we wanted to reproduce in our lab, we selected only 7 of the 16 sequences that were already evaluated, plus 1 sequence for calibration and training of participants. And we choose that based on the SITI, their location in the SITI space, and also this audio characteristic that I just presented before. And we choose for like outdoor scene with crowd and lot of not really clear audio, or like this air drying as well, not really clear, or more like discussion with people, or people playing in park where the sound will be more clear. And also we'll have also some movement because people are walking around the camera or the dog are running around. There I just provided also what we use to have this extract this movement or location of sources. It's just a plugin, a Sparta power map that will give the power map of the audio in the 4th order ambisonic. And what we can see here is the most of the power in the audio is coming from in front of us, from the stage where the musicians are playing, and you have some reverb coming back from the back of the room. And what you can see there in dark blue is probably in between the rows or the cushion or below the camera, where there is no sound coming from. Okay. So about the different HRCs that we cover in that new subjective test is we try to cover well the video and the audio degradation that were already performed in the last study. And so for the video degradation, what is considered is first either a down scaling of the ERP, so from 6K to 4K or 2K, and also encoding of the ERP using H.264 at fixed QP 0, 22, 28, or 34. And for the audio degradation, the reference is the audio file at more than 1 megabit per channel, and we call that the PCM. And the audio degradation comes from the AAC LC audio codec at different kbps bitrate. And in total, in the first experiment, we had 48 HRC to taste for the 16 sequences. And there we will try also to reduce and to select a subset of HRCs to try. And I will present that later. So first, about the different subjective methodology that we try on this consumer grade setup. So the first methodology that we try is ACR HR methodology with a 5-grade ACR scale, no repetition of the sequence, and with a calibration of over 3 PVS from this chamber music sequence with low, mid, and high quality. And we choose that based on the previous study, where we choose the highest quality rated by the observer, and the middle and low based also on this previous experiment. And we converted the raw opinion score to DMOS using this following equation, and we tried to have at least 25 assessors for this test. The second methodology that we try is based on the DCR methodology with the classic 5-grade DCR scale, where you rate the impairment of the present in the video, and you have first the source that is presented, then a 5-second gray screen, and then we display the PVS under test. We choose to take 5-second pause in between to let the people get comfortable again on the chair, and to if they wanted to change a little bit position before exploring the second sequence. So for the different tested HRCs for this ACR, HR, and DCR condition, as I showcased before, we have 48 possible HRCs to select for each of the SRCs. And what we choose to do is to select a subset of 6 video degradation and 4 audio degradation. We choose these 6 conditions, so 6K display at QP0. So this is the reference video that can be combined with any of the audio compression, and then you have the 6K compressed at QP22, and then the 6K downscaled to 4K, and then encoded at QP0, so only the downscaling effect. And all of these HRCs can be combined with the audio SRCs, so the pristine audio, or 64, 32, or 16 kbps per channel. And what you can see here is from the previous experiment that we had, this is the full audiovisual dataset distribution of mean opinion score. And there is the distribution of the mean opinion score that correspond only to this subset of HRCs. And what we can see is that we have more or less exactly the same distribution. So why I showcase that is to try to inface that we are trying to have a balanced playlist or viewing session that will be comparable with what have been done in the previous study. So at the end, for the DCR test, what we obtain is we have 5 SRCs, so 5 sequences that we want to annotate, and we choose for each of these 5 SRCs 6 HRCs to generate 6 PVS, and in total we have 30 PVS to annotate in a viewing session. And we recruited 25 naive assessors for 30 minutes in lab experiment, and on average they only needed 24 minutes to annotate the 30 PVS. After we didn't want it to have too long experiments, since 360 content can or HMD can trigger some motion or some sickness. So that's why we try to keep as short as possible the experiment. And if people wanted during the test to remove the headset and to continue 2 or 3 minutes later, they were allowed to do that. And similarly, for the ACR HR test, in that case, we use the same 5 SRCs plus 2 additional ones, since ACR HR annotation is faster than DCR annotation. And we add the same 6 PVS per SRCs, and also hidden reference. So instead of annotating 30 PVS, in that case, people had to annotate 49 PVS. and that took on average only 19 minutes for participants. And again, we recruited 25 naive assessors for 30 minutes in-lab experiment. Okay, so maybe to recap a little bit this QE condition and what we are comparing. So in the first row is the data that we already had from previous work in this reference setup with 26 channel loudspeaker and also trained assessor that were trained following the procedure described in the cited paper. And the rating scale for this trained assessor was SAMVIC. And us in the in-lab condition and with this consumer grade setup, what we wanted to try is the ACR and DCR rating scale with naive observer. And the sound system is the building headphone of the HMD, and with binaural rendering, assessors are naive, and the rating scale are provided here. So now about more the result and analysis. So first of all, we just roughly check how people are using the scale across these three different condition. So what we can see is that there is a high agreement between ACR naive condition, so in this consumer grade setup, with the DCR naive condition, also in this consumer grade setup. What we can see as well is that the participants are using the scale in a similar range. So it means that this red line that is fitting the data is parallel and just offset by just a factor with the red line that translates a one-to-one relation. And what we can see as well is that the correlation is quite high, and the RMSE between the different stimuli is also quite low. Then when we compare the DCR naive condition with the reference condition of previous work, we can see that the agreement is a little bit lower, but still quite high. So the differences can be also attributed by this pristine condition to play back the audio and the different audio degradation. And what we can see on the last plot is the comparison between the reference setup and the ACR rating in this consumer grade condition setup. And what we can see here is that the red line is not parallel anymore with this one-to-one relationship, and this translates that the scale is used differently between this ACR with naive observer and the SAMVIC scale. And so in that case, this can be attributed also to the difference in the audio playback, but maybe also on the task to use ACR scale to rate the audiovisual quality. Okay, and so to try to dive a little bit more in this analysis and differences, we try to track the most confidence interval. So I already presented that a few hours ago. So here what we are tracking is the mean average CI around the estimated MOS for all the stimuli of the data set, and a smaller score indicates a better overall performances in the data set. And the second indicator is based on this discriminability ratio on mean opinion score. So it's based on the t-test analysis on pair of stimuli MOS. So what we are doing is that we are creating all the possible pair of stimuli, and we are trying to assess. We are assessing if the opinion score below this MOS are statistically different from the distribution of opinion score of another stimuli. And we average all of this all of this significant test into a ratio that, when this ratio is high, is indicate a better discriminability and is a better separation between all the stimuli and the mini opinion score. So when we look at this two indicator on this on the collected data, what we can see is that on the x-axis is the number of assessors that we include in the analysis, and on the y-axis is this most discriminability that we achieve with a certain number of observers. And what we can see is that the reference setup with trained assessor is achieving the highest possible discriminability, and even with a few number of assessor. And what we can see as well is that to achieve a similar discriminability, we need maybe a little bit more than, for instance, with 28 DCR annotator, we achieve the discriminability of only 17 expert assessor. So this is also to compare how many assessors are valuable for each of the different conditions, since we are evaluating the same PVS. And then what we have also is this ACR setup that is performing worse than the DCR when we are using the DCR rating scale, and this is at a fixed number of assessors. And on the other side, you have the similar analysis when you are comparing the confidence interval obtained with different increasing number of assessors. And then what we can do is similar to the presentation a few hours ago, is that we can have a factor that take into account how long do we need to collect the data, and it's also related a little bit to the budget of an experiment, since we need to compensate participants for 2, 4, 6, 8, or 10 hours total work. So dispatches across the 25 or 30 observers that we recruit. So in that case, it's difficult to plot also the reference setup, since we don't have a good estimate about how long people in DTU spend to train the assessor. And also, does it worth it to train assessor to annotate only 30 PVS as we did here? Or does it worth it to annotate, train this assessor when we annotate more than 700 PVS as what was done in the first experiment? So what we can see here also is that ACR, in the ACR, when using ACR, we can benefit from the speed of annotation or the speed at which the annotation are provided by the observer. And we can see that the discriminability is increasing faster and the CR are decreasing faster compared to in the DCR experiment. But what we can see is that maybe there is a tendency where at some point DCR will be better than ACR experiment. Maybe there will be a crossover between these two plots. And this could indicate that DCR on the long run, to achieve high discriminability, to have small CI, is a better metric for this type of multimedia quality assessment compared to ACR. So I just provided this additional slide because actually there in this paper and this talk, I'm more presenting the data from the audio-visual viewpoint, but we have the same, we perform the same experiment without the audio playback. So the people assessor didn't judge the audio part and only judge the video part. And what we can see here is that we are even closer to have this crossover, so that ACR, if we had more ACR participants, it will be not beneficial. It is better if we want to achieve this discriminability to start with DCR participants to achieve higher discriminability. And maybe someone could comment that on this side, it doesn't seem that we will have a crossover. But what I want to emphasize is that maybe, how to say, mean confidence interval is just, how to say, is not what we want to add at the end of an experiment to have just small CI. It's not what we want at the end. What we want at the end of an experiment is, yes, to have a small CI, but a good spread, and we can separate well all the stimuli, because we can achieve really small CI if all the annotators are voting the middle of the scale for any type of PVS. We will have really small CI, but the discriminability will still be really low. So I want to emphasize that maybe discriminability is a better and more important indicator than checking variance or the average confidence interval inside the dataset. And now on the second point of this talk is more about objective metric and resolving power. So why we are targeting that is that currently there is no existing audiovisual quality benchmark on the higher order ambisonic or spatial audio. And also what we want to do is, since we have these ERPs that are 6K or maybe 8Ks, and audio channel that have 26 audio channel to evaluate, we want also to try to address to have a greener metric and more efficient to run on these two modalities. So what we propose is to explore the ITU bitstream and parameter-based method, as well as traditional full reference metric like VMAF and VSCOL for audio, and see how far we are with this ITU lightweight model. So we choose 5 different audiovisual quality metric. So the first one is a combination of VMAF and VSCOL. So we take the VMAF evaluation on the ERPs and combine that with the VSCOL evaluation on the audio stream. And we use the linear combination defined in ITU P1203. .3 that is providing some coefficient to weight audio quality characteristic with video quality characteristic and audio quality characteristic. And then we have a second model that is the P1204M3 combined with VSCOL. So similarly, we use this no reference video quality model and combine that with VSCOL using the parameter provided in P1203.3. And then what we did also is to try to adapt the feature that are used by this parametric model, no reference parametric model. So especially the video bitrate that is really large for 6K 360 content compared to 2D images and 2D videos. And what we use for the scaling is just a simple ratio between the HMD viewport size and the ERP size. So what you have there is 360 degree by 180 degrees of the ERP divided by the viewport side of the HMD, and it's a scaling coefficient that we of 5.35 that we apply on the video bitrate. And once we apply this viewport V if scaling, we can use the P1203 model in mode 0 with 0.35 for the the quality score of the audio, and it's a different temporal pooling compared to O46 that is using the O35 plus a random forest model. So it was two different propositions from two different labs that needed to make up to this ITU recommendation. And then what we suggest as well is to replace this O35 or O48 by the VSCOL score and see how all of that is performing. So here we just do a simple evaluation, checking SRCC coefficient for this different model across the different conditions. So what we can see is that VMAF VSCOL is performing quite well, especially on the DCR naive condition, but not that much in the reference condition. And the model that are competing are performing the best across the different conditions are P1203 mod 0 with the O35 scaled parameter for the viewport of 360 video. And this model are really lightweight compared to VMAF combined with VSCOL. So it's really interesting to have this conclusion. And another thing is that for now there is no retraining or anything, and that we know from some experiment that we run is that if we change the coefficient of linear combination provided by ITUT to pool VMAF and VSCOL, we could achieve better performances that will be more comparable with the one that we achieve with this no reference parameter-based model. And now more about resolving power. So the resolving power of video quality metric can be defined as the difference between two video quality metric values for which we can translate that we have a difference in the subjective score. And this statistical difference is usually evaluated at 95% significance level. So to explain in more detail our resolving power from ITU BT 1676 is performing. So you form all the possible pair of stimuli. So each of the blue dots there are all the possible pair of stimuli that we have in our reference condition, for instance. And then what we perform is this z-test between the pair. And what we plot on the y-axis is the significance result of the z-test between 0 and 1 and sometimes different intermediate value. And then what you can do then is to average across different bin, so different portion of this x-axis, the amount of significantly different pair and the amount of non-significantly different pair, and you have this curve that will increase with the difference in MOS between inside a pair of stimuli. And what you will report is at 95% significance level, the delta that is corresponding to that level. So in that case, for VMAF VSCOL metric, in this reference condition with 21 trained assessor, we have VMAF VSCOL resolving power of 0.3. And this is normalized on the 0 to 1 scale. Maybe just to comment on this 0.3, maybe some people will think that resolving power of 0.3 is quite large. So I check in previous SAM meeting, and I found this analysis of VMAF on the Netflix dataset, where you can see that VMAF has a really high correlation with the subjective data, really low RMSE, and the resolving power in that case is of 23 out of the 100 possible predictive score of VMAP. So it corresponds to a 0.23 resolving power at 95% on this if you scale it to a 0 to 1 scale. And then what we wanted to check is also the evolution of this resolving power with different data accuracy, so with different discriminability level. So what is the resolving power when we only take 12 out of the 21 trained assessors in the reference condition? We can see that this resolving power is higher, since due to the quality of the data that we have, and not because of the metric accuracy of the score. And this is something that maybe can be related to discriminability and explore. So it's what we are presenting here. So the resolving power as a function of discriminability. So discriminability is achieved with more and more participants, and at the end, it's required more and more participants to gain a little bit of discriminability. And what we can see here is that for some of the metric in some condition, to achieve the best possible resolving power, to explain the resolving power of a metric, we need to have really high discriminability to express the full potential of a metric. So, and what you can also see is that with different discriminability levels, so different data accuracy, so the order between different metric can switch and be and a metric can become better with higher discriminability in the data. And what we can also observe is that the P1203 Mod0 model have achieved the best resolving power across all the possible models at the highest possible discriminability in the different conditions. So to conclude, we conducted a comparison between the efficiency of different subjective methodology for quality assessment of 360 audiovisual content with spatial audio. We also try to elaborate more on the that we need high discriminability to extract the best resolving power of objective quality metric. And we try also to suggest a proposal to adapt existing ITU no reference parameter-based model to this type of content, taking into account the viewport size and also the audio, spatial audio. So I think what I can add a little bit more is that we have more data that we collected. I just show one slide, for instance, about when we are just evaluating the quality of the video without the audio playback in the 3 different conditions. So this also could be explored as what is the impact of the presence of audio on the rating and also the rating behavior, because we have also the eye tracking data. So we could showcase if there is some differences in the exploration behavior of participants when they have audio and when they don't have the audio, or also their exploration behavior between ACR or DCR subjective methodology. So if you have any question or you want me to clarify any point, don't hesitate. Thanks.
Thank you very much. Are there any questions? Yeah, maybe we extended the session too long.
Yeah,
it is really interesting, in my opinion, although that we've got all those presentations related so much into that we change a lot, and at the end we don't see so much change, yeah, which is really surprising. Like for me, I would expect that the changes will be much more significant, but maybe it's kind of what kind of change we could have, yeah, like even a more significant change would be very, very difficult to obtain. So maybe this is a little bit an impact of that.
Yeah. So you mean in terms of how to say, in the most or in between the condition, like overall.
Like like you showed the results for which are really like in line with the previous and just little bit shifted, and you really change the devices significantly. Yeah, those are completely different systems.
Yeah.
Well, at least from how I understand it. Yeah, like
like the audio playback is completely different.
Yeah, and the one with the surrounding, it looks like the surrounding doesn't matter. Yeah, on the other hand, I doubt it doesn't matter because all the cinemas, they didn't invest in surrounding audio just for fun. Yeah, so
yeah,
well, or maybe they did.
Yeah,
I don't
after
know.
there is some for some of the stimuli there are differences, and I think it's some next step that we want to try to characterize which stimuli have because maybe per SRCs we could conduct this analysis where we could showcase if some content are more affected by different setup and if some other content are not at all affected by the playback.
You're right. That obviously, the audio analysis is the key here, because if it's not really super surrounding, then well, you have no chance to. And then maybe it can mask the effect, yeah, because then the few points are a little bit away, but still most of the points are somehow in line, and then everything looks like in line.
Yeah. And still, how to say, considering that we are in this high discriminability range, that because some people could conclude there is no differences, but it's just because the data is not of precise enough to showcase the differences. But there we still each time to try to validate that we have a high discriminability, really high confidence in the modes that we have, and to try to then showcase if there is any differences per SRCs or whatsoever.
Yeah, makes sense.
Okay, thanks.
Okay, thank you very much. And I'm seeing no more questions. I would like to close the sum session and give it to Shell, if Shell is still here. Yes.
Yes, absolutely. Okay, thank you all for today. I think it's high time to close the sessions for today. I will thank you all the nice presentation and contribution for all today, and I will also stop the recording. So see you tomorrow, and the same time as today, and for another interesting day. So by that, I close the session.